Have you ever considered how profoundly empty the space between worlds truly is? And yet, through that immense, quiet, dark, tiny traveler's journey for millions, even billions of years, what story would such a traveler tell if its long journey ended here, with us? What would we learn from a messenger that never meant to arrive? Tonight, we will wander through this gentle, hypothetical question together. We will follow the path of a real comet that graced our skies, and then imagine a different ending to its ancient story. But first, allow yourself to settle in. Find the position that feels most restful. Notice the gentle weight of the blankets, the soft support of the pillow. Let go of the day and simply be here in this quiet moment. Before our journey begins, I wonder where you are listening from tonight. If you feel moved to, you might share your city or country in the comments below. It is a quiet comfort to know we are all listening to this story together, under the same vast sky. Our story begins not with a cataclysm, but with a whisper, a faint and patient observation that connects our small world to the great, dark ocean of the outer solar system. In the final days of 2019, long before it held any special significance, it was just a whisper of light, a single, unassuming point, moving with infinite patience against the steady backdrop of distant stars. Down here on the surface of our Earth, the world was turning as it always does, filled with the familiar sounds and rhythms of life. But high above, in the silent, automated observatories that keep a tireless watch over the night, something new had entered the field of view. This discovery was made by a robotic astronomical survey, a set of telescopes in Hawaii designed for a specific and quiet purpose: to scan the heavens for asteroids and comets. The system is called ATLAS, which stands for the Asteroid Terrestrial Impact Last Alert System. Though its name sounds urgent, its work is one of profound patience, night after night, painting a comprehensive and ever-changing map of our celestial neighborhood. And on the 28th of December of that year, the system flagged a new object. It was incredibly faint, a ghost of a traveler, more than 270 million miles away from Earth at the time. To the computer, it was simply a set of coordinates, a velocity, a trajectory. But to the astronomers who reviewed the data, it was the beginning of a story. This is how most comets are found in our modern age. Not by a single person peering through a brass eyepiece for hours, but by sophisticated digital eyes that can detect impossibly faint movements across the vast tapestry of the sky. These systems compare images taken minutes or hours apart, and their software is trained to notice the one tiny speck that has shifted its position relative to the fixed stars. It is a testament to human curiosity, this quiet and persistent search for the wanderers of our solar system. The newly discovered object was given a designation, C/2019Y4. It was a simple, technical name, a catalog number for a visitor that had, until that moment, been completely unknown to us. For the first few weeks, it was just another data point among thousands, its future uncertain. Comets are famously unpredictable. Some flare into brilliance, while others fizzle out and disappear back into the darkness from which they came. But as astronomers continued their gentle, nightly observations, they began to notice something intriguing about this particular faint light. It was brightening, and not just slowly, but with a surprising speed that suggested it was a relatively large and active comet. This initial observation, this first quiet hello from the depths of space, sparked a gentle curiosity in the astronomical community. What was this object? Where had it come from? And what kind of journey had it undertaken to finally grace our skies? These questions set the stage for the next part of its story, a narrative that begins not in our familiar neighborhood of planets, but in the far, frozen frontiers of our solar system, a place we have never seen, but can only imagine. Having found this faint visitor, our minds naturally drift outward, to the place where its long, silent story truly began. To truly understand our faint messenger, we must cast our minds far beyond the orbits of the planets we know, past the rocky belt of asteroids, past the majestic gas giants, Jupiter, Saturn, Uranus, and Neptune. We must journey to a place so distant and so vast that the sun itself would appear as just another bright star in the sky. This is the realm of the Oort cloud. It is not a cloud in the way we think of them on Earth, soft and made of water vapor. It is an immense, spherical shell of icy bodies, a cosmic reservoir that surrounds our entire solar system like a delicate, scattered bubble. Astronomers believe it may contain trillions of comets, each one a pristine relic from the time when the planets were first forming, over 4.5 billion years ago. These are the leftovers, the unused building blocks of our solar system, cast out into the deep freeze of interstellar space by the gravitational pull of the young giant planets. And it is here, in this silent, frozen darkness, that the story of our comet truly begins. For unimaginable lengths of time, perhaps for billions of years, it drifted in a slow, stable orbit within this great cloud. Its existence was one of perfect, cold stillness. It was a sleeping world, its heart a mixture of frozen water, carbon dioxide, methane, and ammonia, all bound together with dust and rock. It knew nothing of the warmth of a star, nothing of the gentle pull of a planet. Its journey was a patient circle at the very edge of the sun's influence. But the universe is never truly still. Even in the profound emptiness of the Oort cloud, there are gentle nudges, tiny gravitational whispers that can change a destiny that has been set for eons. Perhaps it was the passage of a nearby star, its gravitational field just barely brushing against the outer edges of the Oort cloud. Or maybe it was the slow, collective tidal pull of our Milky Way galaxy itself. Whatever the cause, a tiny, almost imperceptible perturbation occurred. A gentle push, no more than a whisper, was enough to disturb the comet's ancient, stable orbit. This subtle change was all that was needed to begin a new journey. The comet's path was now slightly altered, nudged just enough for it to begin a long, slow fall inward, toward the distant point of light that was our sun. This was not a dramatic, sudden plunge. It was an inexorable drift, a journey that would take thousands upon thousands of years to complete. For a human lifetime, its movement would be almost immeasurable. For 100 lifetimes, it would still be in the cold, dark expanse of the outer solar system. Its orbital period was estimated to be around 6,000 years. This means that the last time it may have ventured into the inner solar system, the great pyramids of Egypt had not yet been built, and human civilization was just beginning to write its earliest stories. As it fell, it moved from a world of near-perfect darkness into a world of slowly growing light. For millennia, it traveled in silence. It passed through the vast, empty regions beyond Neptune's orbit, a tiny frozen object in an almost infinite space. The sun grew from a bright star to a small, brilliant disk. The comet was still dormant, still a frozen relic of the past, but it was on a trajectory now, a path set by the immutable laws of gravity that would eventually carry it into the warmth and light of the inner solar system. This journey, a fall of thousands of lifetimes, was a silent pilgrimage from the cold dawn of our solar system's history toward the living present. And as it crossed the threshold of the outer planets, It was no longer just a resident of the distant Oort cloud. It was becoming a visitor, a messenger carrying with it the secrets of its ancient home, preparing to reveal itself to the patient, observers on a small blue world. Now that we have a sense of its grand and ancient voyage, we can return to the moment of its discovery and understand the simple meaning humans gave to it through a name. Every discovery in the cosmos is eventually given a name, a label that transforms it from an anonymous point of light into something we can speak of, study, and share with one another. These names are not poetic or whimsical. They are practical, following a clear and logical system that tells a story all on its own. The designation given to our comet, C/2019 Y4, Atlas, is a perfect example of this quiet, scientific language. Let us gently break it down to understand the simple story it contains. The first letter, C, tells us about the comet's journey. It stands for non-periodic, meaning this comet is not a regular visitor to our inner solar system on a human timescale. Its orbit is so vast and long that for all practical purposes, this is its one and only visit in our recorded history. If it ever returns, it will be in a distant future, thousands of years from now. This single letter immediately places it in a different category from famous comets like Halley, which is a P, or periodic comet, returning every 76 years. Next comes the year of its discovery, 2019. 2019. This anchors the comet in human time, forever linking it to the year that our patient, robotic eyes, first noticed its faint light. It is a simple, humble timestamp on an object that has existed for billions of years. The following letter and number combination, Y4, is a little more detailed. The sky is divided into 24 sections, corresponding to the half-months of the year, and each is assigned a letter of the alphabet. Y signifies that the comet was discovered in the second half of December. The number 4 tells us it was the fourth comet discovered in that specific half-month period. It is a simple, elegant system, like a cosmic library's card catalogue, ensuring that every new visitor has a unique identifier. Finally, we have the name in parentheses, a TLAS. This part of the name honors the discoverer. As we learned, it was not a single person, but the Asteroid Terrestrial Impact Last Alert System Survey. Giving the comet this name is a quiet acknowledgement of the technology and the teams of people who build and operate these incredible tools of discovery. It connects the ancient, cosmic traveler to the modern, human endeavor of understanding the sky. So, while C/2019 Y4, Atlas, might sound like a cold, technical label, it is in fact a compact story. It tells us that a long-period comet was discovered in the last weeks of 2019, the fourth one found in that period, by the Atlas survey. It is a name born of patience, precision, and a global, collaborative effort to map our place in the universe. It is a human fingerprint on a messenger from the void, and understanding it allows us to see not just a comet, but a moment of connection between our world and the vast, silent cosmos beyond. This newfound understanding of its identity in our records sets the stage for the excitement that began to build as it drew ever closer. In the early weeks of 2020, as Comet Atlas continued its steady journey inward, something remarkable began to happen. The faint speck of light that had been discovered just weeks before started to brighten, and it did so at a truly astonishing rate. For astronomers and amateur stargazers, this was a sign of great promise. The brightness of a comet is one of its most captivating and most unpredictable qualities. It all comes down to a process that is both simple and beautiful: the awakening of the comet's icy heart. As a comet travels from the deep freeze of the outer solar system, the sun's radiation becomes increasingly intense. This energy, this gentle warmth traveling across millions of miles of empty space, begins to heat the comet's nucleus. The nucleus, as we know, is a mixture of ice, dust, and rock. The ices are not just water ice, but also frozen gases like carbon dioxide and carbon monoxide, which are much more volatile. As these ices warm, they do not melt into a liquid, because in the vacuum of space, a liquid state is almost impossible to maintain. Instead, they undergo a process called sublimation, transforming directly from a solid into a gas. This outgassing is what gives a comet its life. The jets of gas erupt from the surface, carrying with it a cloud of dust that was trapped within the ice. This expanding cloud of gas and dust forms a glowing atmosphere around the nucleus, which is called the coma. It is this coma that we see from Earth as it reflects sunlight, making the comet appear as a fuzzy, luminous object in the sky. The more active a comet is, the more outgassing occurs, and the larger and brighter its coma becomes. Comet Atlas was outgassing with incredible vigor. Its brightness was increasing so rapidly that early predictions suggested it could become a truly spectacular sight. Some astronomers speculated that by the time it made its closest approach to the Sun in May, it might become visible to the naked eye, perhaps even shining as brightly as some of the most famous stars in our sky. This promise of a great comet happens only a few times in a generation, and the possibility created a quiet wave of excitement that spread around the world. Stargazers began to follow its progress, sharing images and observations of its growing, beautiful green coma. The green color was another lovely detail, a signature of diatomic carbon molecules being illuminated by the sun's ultraviolet light. This was a spectacle in the making, a celestial performance that had been traveling toward us for thousands of years. The initial measurements and the rapid brightening created a gentle narrative of anticipation. It felt as though we were about to witness something truly special, a rare and beautiful visitor making its grand entrance on the cosmic stage. This growing excitement, however, was also intertwined with a deeper scientific mystery about the comet's own history, a connection to a past visitor that made its journey even more compelling. As astronomers plotted the precise trajectory of Comet ATLAS, they uncovered a fascinating piece of its history, a celestial echo from our own past. Its orbit, the specific path it was taking through our solar system, was remarkably similar to that of another comet, a brilliant visitor known as the Great Comet of 1844. This was more than just a coincidence. It was a profound clue about the comet's origins, suggesting that these two objects were not strangers, but long-lost siblings. The Great Comet of 1844 was a spectacular sight. It became brilliantly visible to the naked eye, with a long, graceful tail that stretched across the sky. For the people of that time, it was a source of wonder and awe, a silent, luminous messenger in the pre-industrial skies. They had no way of knowing its composition or its origins, but they recorded its journey with great care. It is through these historical records that modern astronomers can calculate the orbits of past comets with incredible precision. And when they compared the orbital path of C/2019 Y4 at Hellas with that of the 1844 comet, the match was almost perfect. This led to a beautiful and compelling theory that both of these comets are fragments of a single, much larger parent comet that disintegrated long ago. We can imagine that perhaps on its last pass through the inner solar system, some 5,000 or 6,000 years ago, this ancient, giant comet was subjected to immense stress. The sun's heat and gravity may have been too much for its fragile structure, causing it to break apart into 2 or more large pieces. After the breakup, these fragments would have continued on their journey together, traveling along nearly identical orbits, like a silent, celestial family. They would have journeyed out to the farthest reaches of the solar system and then begun their long, slow fall back inward. But because of the slightly different velocities they gained during the fragmentation event, they would not arrive at the same time. The first fragment, the Great Comet of 1844, arrived first, gracing the skies of the 19th century. And now, over 175 years later, the second fragment, Comet ATLAS, was making its own return. This idea of a cometary family transforms our view of Atlas. It was not just a solitary wanderer, but a piece of a larger story, a tangible link to a celestial event that happened thousands of years ago. It deepened the sense of anticipation, as astronomers were not just watching a new comet, but also a reunion of sorts, a chance to study a piece of a body that had last been seen generations ago. This shared history was a key piece of the puzzle, and it introduced the crucial theme of fragmentation, a natural process in the life of a comet that would soon become the most important part of our own story as we continue to follow its journey. As we conclude this first part of our journey, let us pause and reflect on what these messengers truly are. Comets, like our visitor ATLAS, are more than just balls of ice and rock. They are time capsules, ancient libraries holding the chemical secrets of our solar system's birth. When the sun and the planets were just beginning to form from a vast, swirling cloud of gas and dust, these comets were also taking shape in the cold, distant, outer regions. They are made of the primordial material, the very same stuff from which Earth and everything on it was eventually built. The dust within them is ancient, perhaps containing grains that predate our own sun. The water ice they hold is a chemical link to the water in our own oceans. The simple organic compounds locked away in their frozen hearts are the fundamental building blocks that, on our world, eventually gave rise to life. To study a comet is to look back in time, to read a page from the very first chapter of our solar system's story. Their composition is a legacy written in dust and ice, a pristine record that has been preserved in the deep freeze of space for over 4.5 billion years. Comet Atlas carried this legacy with it on its long journey. Its discovery, its name, its promised spectacle, and its connection to a comet from our past all formed the initial chapter of its modern story. We saw it as a faint light, a distant traveler from the Oort cloud. We learned to call it by its scientific name and recognized its kinship with a great comet of the past. We watched with gentle anticipation as its brightness grew, promising a rare and beautiful sight in our night sky. This was the comet as we first knew it, a messenger full of potential and ancient history. We have now set the stage, understanding where it came from and the promise it held. In our next chapter, we will journey with it as it drew closer, following its silent approach toward the sun, where the story would take an unexpected and illuminating turn. Having met our celestial visitor, we now join it on its grand, sweeping journey into the heart of the solar system. This is a chapter about the silent, powerful forces that guide its path and begin to awaken it from its long slumber. Imagine a path drawn across the solar system, not by a pen, but by the invisible hand of gravity. This was the trajectory of Comet ATLAS, a graceful, sweeping arc that carried it from the dark frontiers toward the brilliant light of the sun. The shape of this path is known as a near-parabolic orbit. It is not a closed circle or a gentle ellipse like the orbits of the planets. Instead, it is an open-ended journey, a path of a visitor who has come from a great distance and will return to a great distance, never to be captured into a short, repeating cycle. For the vast majority of its thousands of years-long journey, the comet moved through the immense, quiet spaces of the outer solar system. Here, the sun's gravitational pull is gentle, a constant, faint whisper. The comet's velocity was slow, its progress measured over centuries. It drifted past the orbits of the ice giants, Uranus and Neptune, which would have appeared as nothing more than faint, star-like points of light. It continued its fall inward, crossing the orbit of the great ringed planet, Saturn. Even here, at a distance of nearly 1 billion miles from the Sun, the comet remained mostly dormant, a silent, frozen world. But as it crossed the orbit of Jupiter, the largest planet in our solar system, its journey began to accelerate. It was falling deeper into the Sun's gravity well, that great, invisible depression in the fabric of space-time created by the Sun's immense mass. As it fell, its speed steadily increased, a perfect and silent conversion of potential energy into the energy of motion. From this point onward, its progress was no longer measured in centuries, but in years and then months. This inbound trajectory was perfectly predictable, governed by the same laws of celestial mechanics that dictate the motion of our own moon and the turning of our own world. Astronomers on Earth could calculate its position with incredible accuracy, knowing precisely where it would be weeks or months in the future. They watched as it moved from one constellation to another, a tiny, fuzzy point of light on a predetermined path. There was a profound serenity in this predictability, a sense of cosmic order in its silent approach. The comet was not wandering aimlessly. It was following a course that was set for it by the fundamental structure of our solar system. This graceful, curving path was bringing it ever closer to the Sun, the great central star whose influence was about to transform the comet in a much more dramatic and visible way, awakening it from its frozen sleep. As Comet Atlas journeyed deeper into the inner solar system, crossing the orbit of Mars, it entered a new realm. Here, the Sun was no longer a distant point of light, but a brilliant, powerful star. Its influence felt not just as gravity, but as a palpable warmth. This warmth, this stream of radiant energy flowing constantly outward, is what truly brings a comet to life. We should not think of this as a harsh or violent force, but rather as the Sun's gentle hand, reaching out across millions of miles of empty space to touch the comet's frozen surface. This energy began to gently raise the temperature of the comet's nucleus. For billions of years, its core had remained at temperatures hundreds of degrees below freezing, a state of perfect preservation. But now, that ancient cold was beginning to yield. The first ices to respond were the most volatile ones, the ones that require the least amount of energy to transform. Frozen carbon monoxide, methane, and carbon dioxide, which had been locked in a solid state since the dawn of the solar system, started to feel this gentle warming. They began to sublimate, turning directly from solid ice into invisible gas. This process didn't happen uniformly across the entire surface. The nucleus of a comet is not a perfect, smooth sphere. It is an irregular, lumpy body with areas of light and shadow. Some parts of the surface might be covered in a thick layer of dark, insulating dust, while other areas might have fresh, exposed ice. The outgassing began at these weaker, more exposed points. Fissures and cracks in the surface became vents, and from them, jets of gas began to stream out into the vacuum of space. These jets were like tiny, silent geysers, releasing the pressure that had been building up just beneath the surface. As these gases streamed away from the nucleus, they did not simply disappear. They carried with them fine particles of dust that had been mixed in with the ice for billions of years. This mixture of gas and dust created a vast, glowing cloud around the nucleus, an atmosphere that is called the coma. It was this coma, illuminated by the sun, that astronomers on Earth were watching with such interest. The size and brightness of the coma were a direct measure of the comet's activity. As Atlas drew closer to the Sun, the outgassing became more and more vigorous, and its coma swelled to an enormous size, at one point estimated to be larger than the Sun itself. The solar wind, a constant stream of charged particles flowing from the Sun, began to push against the gas in the coma, sweeping it back into a long, straight, glowing ion tail. The slightly heavier dust particles were less affected and formed a second, gently curving dust tail. The Sun's gentle hand was painting a masterpiece in the sky, transforming a dark, inert block of ice and rock into a beautiful, luminous object with two magnificent tails stretching for millions of miles. This glorious transformation, however, was also a sign of the immense forces that were beginning to act upon the comet, forces that would soon test its very structure as it danced with the other great bodies of the solar system. While the Sun was the primary conductor of the comet's journey, the other planets also played their own subtle, quiet roles. The solar system is not an empty stage with a single, central actor. It is a dynamic system, a family of massive bodies all engaged in a silent gravitational dance. As Comet Atlas swept inward, it felt the gentle, persistent pull of each of the giant worlds it passed. Far out, as it crossed the paths of Neptune and Uranus, their influence was minuscule, a nearly imperceptible tug on its long trajectory. But as it neared the orbits of Saturn and, most significantly, Jupiter, these gravitational whispers became more pronounced. Jupiter, the king of the planets, possesses a gravitational field so immense that it acts as a great shepherd for the solar system, shaping the orbits of countless asteroids and comets. A close encounter with Jupiter can dramatically alter a smaller body's path, either flinging it out of the solar system entirely or capturing it into a much shorter orbit. Comet Atlas did not make a particularly close pass by Jupiter on this journey, but it still felt its presence. The giant planet's gravity exerted a subtle, continuous pull, slightly bending the comet's path. Think of it as a river flowing toward the sea. The main current is powerful and directs the flow, much like the Sun's gravity. But a large island in the river will cause the water to gently curve around it, a local deviation in the larger flow. The planets are like these islands in the river of space-time, their mass creating gentle curves and eddies in the paths of smaller travelers. These gravitational interactions are a fundamental part of the cosmic dance. They are a quiet conversation between worlds, spoken in the universal language of gravity. For Comet Atlas, these planetary nudges were not dramatic enough to fundamentally change its destiny on this particular visit, but they are a reminder of the interconnectedness of the solar system. Every object, no matter how large or small, contributes to the overall gravitational field. The path of our comet was the sum of all these influences, the dominant pull of the Sun, shaped and refined by the gentle gravitational tugs of the planets. This dance with the planets was a quiet and graceful aspect of its journey, a reminder of the complex and interwoven forces that govern the heavens. As it continued on its path, refined by these interactions, its appearance from our earthly vantage point continued to evolve, and observers here began to notice the first hints that its brilliant performance might be coming to an unforeseen end. While the comet was performing its silent dance in the cold expanse of space, down on Earth, a very different kind of activity was unfolding. A global community of observers, both professional astronomers with powerful telescopes and dedicated amateurs in their backyards, were all turning their attention to this promising visitor. There is a special kind of connection that forms around a bright comet, a shared sense of wonder that transcends borders and languages. In the early months of 2020, as Atlas continued its dramatic brightening, this community was buzzing with a quiet excitement. Online forums and astronomy websites were filled with daily updates, images, and measurements of its progress. Each new photograph revealed more detail: the beautiful, ethereal green of its coma, the faint hint of a developing tail, and its steady movement against a new backdrop of stars each night. This was a collective, patient observation, a global vigil kept by thousands of people who were all looking up at the same distant object. The professionals at their large observatories were using sophisticated instruments to analyze the light from the comet, breaking it down into its constituent colors to understand its chemical composition. They were measuring the rate of gas and dust production, trying to build a scientific picture of what was happening on the surface of this tiny, distant world. The amateur astronomers, with their smaller telescopes and cameras, were playing an equally vital role. They were the ones providing the constant, nightly monitoring of the comet's brightness and appearance. Their sheer numbers and geographic distribution meant that the comet was being watched almost continuously from somewhere on Earth. For a time, the story was one of simple, beautiful progression. Each night, the comet seemed a little brighter, a little more impressive. The narrative that was building was one of crescendo, of a celestial performance that was heading towards a spectacular climax in late May. People were beginning to make plans to travel to dark sky locations, hoping to witness what could be the brightest comet in decades. This act of watching from afar, of sharing in a collective experience of wonder, is one of the most peaceful and unifying aspects of astronomy. It connects us not just to the cosmos, but to each other. We were all sharing in the same silent story unfolding millions of miles away. But as March drew to a close, the dedicated observers who had been tracking it so faithfully began to notice something subtle, a change in the rhythm of its brightening, a first quiet sign that the story was about to change course. In the final week of March 2020, the steady, triumphant brightening of comet ATLAS began to slow. At first, it was a subtle change, something that could have been attributed to simple variations in its outgassing. Comets are known for their unpredictable behavior, and short lulls in their activity are not uncommon. The community of observers watched with patient curiosity, expecting the comet to resume its upward trend. However, it did not. The brightening stopped entirely. And then, in the first days of April, the unthinkable happened. The comet began to fade. The point of light that had been growing with such promise night after night started to become dimmer. This was a profound and unexpected turn in the narrative. The crescendo had ceased, and a gentle, quiet decrescendo had begun. For the astronomers who had been following its journey, this was a clear signal that something fundamental had changed within the comet. The engine that was driving its brilliant display, the sublimation of ice from its nucleus, was faltering. The great spectacle that had been promised was now in doubt. This dimming was not a sudden event, but a gradual, gentle fading, as if a candle in the distance was slowly being extinguished. This faltering light was the first piece of direct evidence that the immense forces the comet had been enduring on its journey inward were finally taking their toll. The sun's warmth and the subtle gravitational stresses had been testing the comet's structural integrity all along. The dimming suggested that the nucleus had reached its breaking point. This gentle shift in the story, from one of growing brilliance to one of quiet fading, marks a crucial transition. It leads us away from the promise of a great spectacle and toward a deeper understanding of the comet's true nature, its inherent and profound fragility. We will now explore this delicate heart of our visitor in the next chapter. The unexpected fading of comet ATLAS guides our attention inward to its very core. To understand why its light faltered, we must journey to the heart of the comet itself and explore the beautiful, delicate, and ancient materials from which it was made. At the center of the glowing coma, hidden from our direct view, lies the heart of the comet, the nucleus. For decades, astronomers have used a wonderfully simple and evocative phrase to describe this object: a dirty snowball. This gentle metaphor, first proposed by the astronomer Fred Whipple in 1950, beautifully captures the fundamental essence of a comet's core. It is a mixture of things we find familiar, ice, dust, and rock, but in a form that is truly ancient and primordial. Let us imagine we could hold this nucleus in our hands. It would not be a smooth, solid ball of ice like we might imagine. It would be an irregularly shaped object, perhaps resembling a lumpy potato or two smaller objects gently fused together. Its size would be surprisingly small, perhaps only a few miles across, a tiny world unto itself. The snowball part of the name refers to the ices. This is not just the frozen water we know, but a cocktail of other frozen substances that could only have condensed in the incredible cold of the outer solar system billions of years ago. There would be carbon dioxide ice, what we call dry ice, and frozen carbon monoxide, methane, and ammonia. These are the volatile materials, the substances that will spring to life under the warmth of the sun. The dirty part of the name comes from the other materials mixed in with these ices. There would be fine particles of dust, silicate minerals much like sand, but in a form that has remained unchanged since the solar system's birth. And most intriguingly, there would be dark, carbon-rich, organic compounds. These are not signs of life, but they are the fundamental, carbon-based molecules that are the building blocks of life as we know it. This dark material is what gives the surface of a comet's nucleus its incredibly low albedo, meaning it reflects very little light. In fact, a cometary nucleus is one of the darkest objects in the solar system, blacker than coal. This dark surface is a very efficient absorber of the sun's heat, which helps to drive the sublimation process that lies just beneath the crust. This primordial snowball is a time capsule. It is a sample of the original solar nebula, the great cloud of gas and dust from which everything in our solar system was born. It has been preserved in the deep freeze of space for over 4.5 billion years, a pristine relic of a bygone era, unlike the planets, which have been heated, melted, and reformed by geological processes. The material in a comet is largely as it was in the very beginning. Its fragile, icy composition is both the source of its beauty and the cause of its vulnerability. It is this delicate balance of ancient materials that allows it to create a magnificent coma and tail, but it is also what makes it susceptible to the very forces that bring it to life, as we will now explore. We have spoken of sublimation as the process that awakens a comet. But let us now spend a quiet moment to appreciate its gentle yet powerful nature. Sublimation is a beautifully simple physical process, the direct transition of a substance from a solid to a gas without ever passing through a liquid phase. It is something that happens on Earth, for instance, when dry ice turns into carbon dioxide vapor. But in the near-perfect vacuum of space, it is the dominant way that ices behave when heated. For Comet Atlas, as it drew closer to the sun, the energy from sunlight was absorbed by its dark, dusty surface. This warmth did not just stay on the surface, it slowly conducted its way into the layers just beneath. Here in the shallow subsurface lay the ancient, volatile ices. As the temperature rose past the sublimation point for each type of ice, first the carbon monoxide, then the carbon dioxide, and finally the water ice, these solid materials began to transform into gas. This transformation created pockets of gas pressure just beneath the comet's crust. Where the crust was weak or porous, this gas would find a path to the surface and escape, forming the jets that we observe. These jets are the engines of the comet's activity. As the gas streams away from the nucleus at high speed, it carries with it the fine dust particles that were embedded in the ice. This is the crucial link between the invisible process of sublimation and the visible spectacle we see from Earth. The gas itself is largely invisible, but the dust it carries catches the sunlight, creating the bright, glowing coma. The more energy the comet receives from the sun, the faster the rate of sublimation, and the more gas and dust are released. This is why the comet brightened so dramatically on its initial approach. The power of sublimation was in full force, creating a vast and beautiful atmosphere around a nucleus that was only a few miles across. The coma could swell to be hundreds of thousands or even millions of miles in diameter, all fed by this gentle, continuous conversion of ancient ice into gas. But this process, as beautiful as it is, also exerts a force on the nucleus itself. The outgassing is often uneven, which can cause the nucleus to spin or tumble. The release of material also means the comet is slowly losing mass, fading away with each pass of the sun. The power of sublimation is a double-edged sword. It is the source of a comet's splendor, but also the engine of its eventual demise, especially given the fragile way in which these primordial snowballs are constructed. When we imagine a dirty snowball a few miles across, we might instinctively think of it as a solid, monolithic object, like a giant piece of rock-hard ice. But the reality of a cometary nucleus is something far more delicate and ethereal. Decades of research and close-up observations from space missions have revealed that cometary nuclei have incredibly low densities. They are not solid, compact bodies, but rather light, porous, and fragile structures. The average density of a known comet is estimated to be about 0.6 grams per cubic centimeter. To put that into perspective, water has a density of 1 gram per cubic centimeter. This means that if you could place a piece of a comet's nucleus in a vast cosmic ocean, it would float. This low density tells us that the nucleus is not a solid block of ice and rock. Instead, it must be filled with empty space. The structure is likely more akin to a loosely packed snowball or a piece of cosmic honeycomb than a solid rock. This fragile structure is a direct consequence of how comets were formed in the early solar system. They were not created in a violent, high-pressure environment. Instead, they grew through a process of gentle accretion, where tiny, icy dust grains slowly and softly bumped into each other and stuck together. This process, happening over millions of years, built up the kilometer-sized nuclei we see today. But it was a gentle construction, leaving a great deal of empty space or porosity between the aggregated particles. The result is a rubble pile, a loose agglomeration of smaller pieces held together by their own very weak gravity, and perhaps some sticky organic compounds. This understanding of the comet's structure is absolutely crucial to our story. A solid, monolithic body would be able to withstand immense physical stress, but a porous, low-density rubble pile is inherently fragile. It has very little internal strength. It can be pulled apart with relative ease. This inherent structural weakness is a defining characteristic of comets. They are beautiful and ancient, but they are not built to last in the harsh environment of the inner solar system. Their very construction, a gentle coming together of primordial particles, makes them vulnerable to the powerful forces they are destined to encounter on their journey toward the sun. These forces would soon begin to test the limits of this fragile structure. As Comet Atlas journeyed closer to the sun, its fragile, low-density structure was subjected to an array of immense and competing stresses. These forces, born from the sun's proximity, began to probe the weaknesses in its ancient construction, testing the delicate bonds that held it together. The first and most obvious stress was thermal. The sun does not heat a comet evenly. The nucleus is constantly rotating, meaning one side is baked in intense sunlight while the other faces the cold darkness of space. This creates extreme temperature differences across the surface and just beneath it. The rapid heating and cooling causes the materials of the comet to expand and contract, creating powerful internal stresses, much like a glass that shatters when hot water is poured into it too quickly. These thermal shocks can create deep fissures and cracks, weakening the overall structure of the nucleus. The second form of stress came from the outgassing itself. As we have learned, the sublimation of ice beneath the surface creates pockets of high-pressure gas. When this gas erupts in jets, it can exert a powerful, uneven force on the nucleus. If the outgassing is particularly violent or asymmetric, it can increase the comet's spin rate. If the comet spins too fast, the centrifugal force can literally tear it apart from the inside out. The very process that makes the comet beautiful is also a source of self-destructive stress. Finally, there are the gravitational tidal forces. Just as the moon's gravity creates the tides in Earth's oceans, the sun's immense gravity exerts a tidal force on a comet. It pulls more strongly on the side of the nucleus facing the sun than it does on the far side. This difference in gravitational pull creates a stretching force, constantly trying to pull the comet apart. For a strong, solid body, this tidal stress is easily manageable. But for a low-density, fragile rubble pile like a comet, this constant stretching can be the final straw, the force that overcomes the weak internal bonds holding the ancient pieces together. These combined stresses, thermal shocks, internal gas pressure, and gravitational tides created a hostile environment for our fragile visitor. The heart of the comet, which had been in a state of perfect stillness for thousands of years, was now being squeezed, heated, and stretched by the powerful forces of the inner solar system. And so we can now see the complete picture of the comet's inherent fragility. We began with its composition, a primordial mixture of volatile ices and dust, a recipe for beautiful but unstable activity. We then understood its structure, not as a solid rock, but as a light, porous rubble pile, a loose collection of ancient building blocks with very little internal strength. And finally, we saw the immense stresses that the inner solar system brought to bear upon this delicate construction. The thermal shocks, the internal gas pressures, and the relentless tidal pull of the sun. When you combine a volatile composition with a fragile structure and subject it to overwhelming external forces, the outcome is almost inevitable. The story of Comet ATLAS was not one of a sudden, unexpected failure. It was the story of a gradual, graceful, and ultimately unavoidable unraveling. The forces that were making it so brilliantly bright were the very same forces that were patiently pulling it apart. Each jet of gas that erupted from its surface was both a part of its glorious display and a symptom of its slow disintegration. Each crack that formed from thermal stress was a step closer to its end. This was not a story of weakness, but simply a story of nature. Comets are born of gentle processes in the cold and quiet of the outer solar system. They are not designed for the heat and gravitational intensity near a star. Their journey inward is a beautiful but ultimately unsustainable performance. This gentle understanding of its inherent nature allows us to view its fading light not as a disappointment, but as a natural and poignant chapter in its long and ancient story, a quiet ghost of the spectacle that might have been. Reflecting on the journey of Comet Atlas up to this point, we can see it as a story of immense promise and quiet dissolution. For a few brief months, it held the attention of the world, a celestial bud that seemed ready to blossom into a once-in-a-generation flower in our night sky. The rapid brightening, the beautiful green coma, and the connection to a great comet of the past all built a narrative of hopeful anticipation. We were preparing to witness a great spectacle, a luminous performance that had traveled for millennia to reach us. But the universe, in its serene indifference, follows its own script, written in the language of physics. The comet's inherent fragility a quality born from its gentle formation in the primordial solar system, meant that it could not withstand the very forces that were making it so beautiful. The sun's embrace was both life-giving and destructive, and so the blossoming never fully occurred. Instead, we witnessed the bud gently fall apart before it could open. The faltering and fading light of the comet was the quiet end of that promise. It became a ghost of what might have been, a celestial echo of a great spectacle that now existed only in our imaginations. There is a quiet beauty in this, a gentle lesson about the transient nature of cosmic phenomena. Comets are like magnificent, ephemeral ice sculptures. Their beauty is inextricably linked to the fact that they are melting, that they are slowly disappearing before our very eyes. We are privileged to witness a small part of their long, slow process of returning to the dust from which they came. The story of Atlas's approach and its fading light closes the loop on why it appeared so promising, only to disappoint those who longed for a brilliant display. Its composition was rich and volatile, leading to the initial surge in brightness, but its structure was too fragile to sustain that activity under the growing stress. This understanding allows us to appreciate the comet, not for the spectacle it failed to become, but for the beautiful and profound scientific story it told us in its final act, the story of its own quiet unraveling, which we will witness next. The fading of the comet's light was not an ending, but a transformation. We now move from watching a single object to observing a graceful and silent process of dissolution, a quiet unraveling that taught us more about the nature of comets than a brilliant display ever could have. In early April of 2020, as the comet continued to dim, astronomers watching through powerful telescopes began to see why. The single, sharp point of light at the heart of the coma, the nucleus, had begun to change. It was elongating, losing its sharp definition. And then, over the course of a few days, it resolved into not one, but several distinct, smaller points of light. This was the moment of collapse, the gentle, quiet fragmentation of the comet's heart. We must not imagine this as a violent explosion. There was no sound, no sudden burst of energy. It was a slow, graceful, and silent process of separation. The weak gravitational and chemical bonds that had held the primordial rubble pile together for billions of years had finally been overcome by the relentless stresses of the inner solar system. The nucleus, that single, lumpy object just a few miles across, simply fell apart. The pieces, which had been nestled together since their formation, now gently drifted away from each other, each one becoming a tiny, independent comet in its own right. Observations from the Hubble Space Telescope provided the clearest view of this serene event. The images it captured were breathtaking in their detail. They showed not just 2 or 3 pieces, but a cascade of fragments. On April 20th, Hubble resolved roughly 30 distinct pieces. A few days later, on the 23rd, it saw 25. Some of these fragments were as large as a house, all of them enveloped in a shared, sun-swept tail of dust. The appearance of the fragments changed from day to day, perhaps because they were tumbling, catching the sunlight like twinkling lights on a distant, festive tree. This was a profoundly important moment for science. While comet fragmentations are thought to be common, they are rarely observed in such detail, especially for a comet that had been so bright and well studied on its approach. We were witnessing, in real time, the primary way that comets are thought to end their lives, not by crashing into a planet, and not by burning up in the sun, but by quietly disintegrating into a shower of smaller pieces, their substance slowly returning to the solar system. The moment of collapse was not a moment of destruction, but one of beautiful and informative transformation, creating a new and ethereal shape in the sky. After the gentle collapse of the nucleus, the newly formed fragments did not scatter in all directions. Instead, they continued to travel along the same orbital path that the parent comet had been following. Because of the very small velocities they gained during the separation, they began to slowly spread out along this path, forming a beautiful and evocative shape. A string of pearls. This serene image perfectly captures the visual aftermath of the fragmentation. Imagine a delicate, invisible thread stretching across space, tracing the comet's original orbit. Along this thread, the individual fragments were now strung out like luminous pearls on a necklace. Each pearl was its own tiny world, a house-sized chunk of the original nucleus, complete with its own small, glowing coma and a faint tail of dust and gas. Together they formed a procession, a silent, graceful funeral march for the comet that had once been. This celestial necklace was a dynamic and ever-changing object. The fragments were not fixed in their positions. They were slowly drifting farther and farther apart, the string stretching and elongating with each passing day. Some of the smaller fragments were likely fading faster than the larger ones, their limited supply of ice sublimating away more quickly. The view through a powerful telescope was no longer of a single, fuzzy object, but of a ghostly, elongated smudge of light, a faint and beautiful testament to the comet's recent transformation. This string of pearls phenomenon is a classic signature of a tidally disrupted comet. Perhaps the most famous example was Comet Shoemaker-Levy 9, which was torn apart by Jupiter's gravity in 1992 and formed a spectacular train of fragments that eventually impacted the giant planet 2 years later. Comet Atlas, however, wasn't disrupted by a planet, but by the gentler, more persistent forces of the sun. Its string of pearls was a more delicate and ethereal creation, a quiet dissolution in the empty space between the planets. This beautiful, transient formation of a celestial necklace provides a perfect, gentle image to hold in our minds as we consider the immediate consequence of this breakup, the inevitable fading of the comet's collective glow. The fragmentation of the nucleus into a string of smaller pieces directly explains why the comet's light began to fade so noticeably. While it might seem counterintuitive that breaking a bright object into many pieces would make it dimmer overall, it all comes down to the science of sublimation and surface area. A single, large nucleus has a relatively small surface area compared to its total volume. This means that only the ice on or near the surface can be heated by the sun and sublimate into gas. The vast majority of the ice is locked away deep inside, too cold to contribute to the coma. But when that single nucleus breaks apart into dozens of smaller fragments, the situation changes dramatically. The total amount of surface area that is exposed to the sun's warmth increases enormously. For a very brief period, this fresh exposure of ice might have caused a small, temporary surge in brightness as all the new surfaces began to outgas at once. But this effect was very short-lived. The much more significant consequence was that the comet's fuel supply, its reserve of ice, was now divided among many small bodies. Each house-sized fragment contained only a tiny fraction of the original comet's ice. These small reservoirs of volatile material were quickly exhausted. They sublimated away rapidly, and once the easily accessible ice was gone, the outgassing from that fragment would cease. So, while there were now many sources of light instead of one, each source was incredibly weak and short-lived. The overall result was a rapid decline in the total amount of gas and dust being produced. The magnificent shared coma that had enveloped the fragments began to dissipate, thinning out and reflecting less and less sunlight. The collective glow of the celestial necklace grew fainter with each passing day. The comet was, in essence, burning through its remaining fuel at an unsustainable rate. The fading glow was the quiet, inevitable consequence of its own dissolution. a gentle and predictable end to its brief moment of brilliance. This real-world fading now allows us to appreciate the valuable lessons learned from watching this process unfold. The journey of Comet Atlas, from its promising brightening to its quiet disintegration, was more than just a celestial spectacle that wasn't to be. It was a profound and unexpected scientific gift. By watching the comet disappear, astronomers learned more about the nature of comets than if it had simply put on a brilliant show and then faded away intact. First and foremost, the event provided a rare, detailed look at the process of cometary fragmentation. It reinforced the idea that comets are not monolithic bodies, but fragile rubble piles, loosely bound collections of smaller, icy chunks. The way Atlas fell apart into a cascade of small fragments, rather than just splitting into 2 or 3 large pieces, was a powerful confirmation of this model. It showed that the forces holding these primordial bodies together are incredibly weak and can be easily overcome. The timing of the breakup was also deeply informative. Comet Atlas disintegrated when it was still quite far from the Sun, farther away than the Earth's own orbit. This was unusual. Most comets that break up do so much closer to the Sun, where the thermal and tidal stresses are at their absolute maximum. The fact that Atlas fell apart so early in its approach suggested that it was exceptionally fragile, even for a comet. This provided a valuable new data point for scientists who model the structural integrity of these ancient objects. It gave them clues about the internal composition and structure of a specific type of long-period comet. Furthermore, because of its connection to the Great Comet of 1844, the story of Atlas offered insights into the evolution of cometary families. The fact that this fragment disintegrated, while its sibling apparently survived its own passage through the inner solar system, raises interesting questions. Was Atlas a weaker piece of the original parent body, or had its structure been weakened over the intervening millennia? These are the quiet, patient questions that drive science forward. The disappearing comet left behind a trail of valuable clues, a rich dataset that will be studied for years to come. It was a gentle reminder that even in an apparent failure, in the ghost of a spectacle, there is profound knowledge to be found. It taught us that sometimes the most important stories are told not in a brilliant flash of light, but in a quiet, graceful fading into the dark. And so, the factual story of Comet C/2019 Y4, Atlas, comes to its gentle and quiet conclusion. The string of pearls continued to spread out along its orbital path, each fragment growing dimmer and dimmer. By mid-May of 2020, the comet had become so faint and diffuse that it was no longer visible, even with large telescopes. The fragments, now inert and silent, continued their journey past the Sun and began their long, slow climb back out toward the deep freeze of the outer solar system. They will not return for another 5,000 or 6,000 years, and when they do, they will be a sparse, invisible shower of cold, dark rocks. Our real journey with this comet is over. We have followed it from its discovery as a faint light, through its period of great promise, to its final, graceful dissolution. We have seen how its story was shaped by its ancient origins in the Oort cloud, its fragile composition, and the immense forces of the inner solar system. Its tale was not the one we expected, but it was a beautiful and illuminating one nonetheless. It was a story of transient beauty, of inherent fragility, and of the quiet, patient process of scientific discovery. Now, as the real fragments of Comet A/TLAS drift silently back into the cold and the dark, we are going to do something different. We are going to pause our own story at a crucial moment and gently step onto a different path. We will leave the world of what actually happened and enter the world of what if. This is a quiet and serene thought experiment. We are not seeking drama or excitement, but a deeper understanding of our own world. Let us now take a gentle breath, and together we will explore the tale of two paths. Here, our journey takes a turn. We leave the path of history and gently step onto a trail of imagination. This chapter is the calm and quiet gateway to our hypothetical exploration, setting the stage for a deeper understanding of our planet and its place in the cosmos. Let us return in our minds to that moment in its journey, just as Comet ATLAS was approaching the inner solar system, still whole and bright with promise. In reality, we know its fragile structure was about to yield to the sun's gentle but relentless pressure. But now, we will imagine a slight difference in its story. This is our point of divergence, the place where our new path begins. Let us quietly imagine that this particular comet was just a little bit stronger. Not a solid rock of iron, but simply a slightly more compressed, more consolidated collection of ice and dust. Perhaps in its primordial formation, the gentle collisions that built it were just a little less gentle, packing the material together with a bit more firmness. Or maybe the ices within it contained a substance that acted like a stronger cosmic glue, holding the rubble pile together with more tenacity. This is a small change, a subtle alteration in its fundamental nature. It is not a dramatic rewrite of its history, but a gentle nudge onto a parallel track. In all other respects, the comet remains the same. It is still on the same trajectory, a graceful arc carrying it toward the sun. It is still the same size, with the same volatile composition. The only difference is this quiet, inner strength, a resilience that will allow it to face the coming challenges in a slightly different way. This simple premise, this idea of a slightly more robust visitor, is the key that will unlock the rest of our gentle, hypothetical journey. Let us hold this thought in our minds as we explore what this small difference would mean for the comet's fate. With this imagined resilience, the story of the comet's approach to the sun unfolds in a different way. The stresses that caused the real Atlas to disintegrate are still present, but now our hypothetical comet is able to withstand them. Let us gently revisit these forces and see how a more resilient core would change the outcome. The thermal stresses, caused by the rapid heating and cooling of the rotating nucleus, still create immense pressure within its structure. Cracks and fissures may still form on the surface, but in our new scenario, they do not propagate all the way through the core. The stronger bonds between the icy grains and dust particles are able to arrest the fractures, preventing a catastrophic failure. The comet groans and shifts under the thermal strain, but it holds together. The internal gas pressure from the sublimating ices still builds up beneath the surface. Jets of gas and dust still erupt into space, creating the beautiful coma and tail. In fact, because the nucleus remains intact, the outgassing can continue in a more stable and sustained way. The comet's brightness does not falter. Instead, it continues to increase steadily, just as the early predictions had suggested. It is on track to become the brilliant spectacle that had been so eagerly anticipated. And finally, the gravitational tidal forces from the sun still exert their gentle, stretching pull. The comet is elongated and stressed by this constant tidal force, but again, its more resilient core resists. The internal strength of the nucleus is just enough to overcome the sun's attempt to tear it apart. It bends, but it does not break. This new narrative is one of endurance. Our hypothetical comet is a survivor. It is navigating the most hazardous part of its journey and emerging intact. This single small change, a slightly denser, more consolidated core, has completely altered its destiny. It is no longer a story of quiet dissolution, but one of steadfast passage. This resilience is the scientific foundation of our thought experiment. By allowing the comet to remain whole, we have kept it on a path that will now carry it through the inner solar system as a single, significant object, setting the stage for the next, crucial turn in our imagined tale. Let us now travel with our stronger, more resilient comet as it passes that crucial point in its orbit where its real-life counterpart fell apart. In our new story, there is no fragmentation. There is no string of pearls, no fading glow. Instead, the single point of light at the heart of the coma remains just that. Single and growing ever brighter. As it moves through the space where the real ATLAS ceased to be, our comet continues its majestic, silent journey. It is now a truly magnificent sight in our hypothetical sky. Its coma is vast and luminous, a great, glowing green sphere in the heavens. Its tails, both the straight blue ion tail and the gently curved white dust tail, stretch for millions of miles behind it, a celestial banner marking its passage. On our imagined Earth, stargazers are not met with disappointment, but with a sense of profound awe. The comet is fulfilling its promise, becoming a great comet, a sight that will be remembered for generations. It continues on its graceful arc, sweeping ever closer to the sun. The outgassing is now at its peak, a constant, powerful release of the ancient material from its nucleus. The comet is a brilliant, dynamic object, a testament to the power and beauty of these celestial visitors. It is a living, breathing world, shedding its substance to create a temporary masterpiece in the sky. This image of an intact, brilliant comet is essential for our journey. We have gently guided our traveler past its moment of real-world failure and kept it on a path of continued brilliance. It is now a single, substantial object, moving at an incredible speed through the most crowded and gravitationally complex part of our solar system. This sustained integrity is what allows for the next, gentle twist in our tale, a subtle change in its trajectory that will set it on a completely new and unexpected course. Its journey as a single, whole object is about to be subtly, but profoundly, altered. In the serene and predictable dance of the cosmos, paths are governed by gravity. For our hypothetical comet, which has so far survived its journey intact, its trajectory is still a smooth, predictable arc, shaped primarily by the sun. However, the inner solar system is a place of many subtle gravitational influences. In our imagined story, we will now introduce one final, gentle, and purely hypothetical event that will alter the comet's destiny forever. Let us imagine that on its path, the comet has a close encounter, not with a planet, but with a smaller, unseen object. Perhaps it is a large, dark asteroid, a resident of the main belt that just happens to be crossing the comet's path at the perfect moment. Or maybe it is another, smaller cometary fragment from a different family, traveling on its own lonely orbit. The identity of this object is not important. What matters is its gentle, gravitational influence. This is not a collision. The two bodies do not touch. They simply pass near each other, a silent and fleeting encounter in the vastness of space. During this close pass, their gravitational fields interact. The smaller body is thrown onto a new course, but our much more massive comet is also affected. It receives a tiny gravitational nudge, a subtle push that is almost immeasurable. This is a concept known in celestial mechanics as a gravitational assist, but on a much smaller and more delicate scale. The encounter ever so slightly changes the comet's velocity, and therefore its trajectory. This change is infinitesimal. For an observer watching from millions of miles away, the comet's path would appear completely unchanged. It would still seem to be on its safe, sweeping orbit around the Sun. But in the precise mathematics of orbital mechanics, even the smallest change can have profound consequences over great distances. This tiny nudge, this whisper of a gravitational interaction, has placed the comet on a new and fateful trajectory. It has been deflected just enough that its path, days or weeks later, will now intersect with the orbit of our own planet, Earth. This is not a random or chaotic event, but a beautiful illustration of how the quiet, unseen forces of gravity can shape cosmic destinies. It is a serene unfolding of physical laws, a silent and elegant shift in the celestial dance, which now sets our comet on a final, gentle collision course. And so, the stage for the remainder of our journey is now fully and gently set. We have taken a real comet, ATLAS, and in our imagination, we have endowed it with a slightly stronger core. This resilience allowed it to survive its journey into the inner solar system intact, becoming the brilliant spectacle it was once predicted to be. We then introduced a quiet, hypothetical gravitational encounter, a gentle nudge that has subtly altered its path. These two small changes have created a new reality for us to explore. Our beautiful, intact comet is now on a trajectory that will lead it to Earth. It is important, as we move forward, to hold in our minds that this is a pure thought experiment. We are leaving the world of astronomy and gently entering the realm of planetary science. Our goal is not to imagine disaster, but to explore, in a calm and serene way, how our planet responds to such an event. We are using this hypothetical scenario as a tool for understanding, a gentle lens through which we can appreciate the immense and beautiful physical processes that govern our world, from its deep oceans to the highest layers of its atmosphere. Let us now proceed with a sense of quiet curiosity. We are not telling a story of fear, but a story of science, a story of the Earth itself as a living, dynamic system. We will follow our visitor on its final approach and witness the serene, impersonal, and ultimately beautiful unfolding of physics. Before our visitor arrives, we must first understand the invisible landscape it is about to enter. This chapter is about the silent, powerful forces and the precise, unseen pathways that will guide the comet on the final leg of its immense journey. As our hypothetical comet now travels on its altered course, its ultimate destination is shaped by one of the most fundamental and beautiful forces in the universe: gravity. We often think of gravity as a pull, a force that reaches out and grabs things. But a more serene and accurate way to imagine it is as a landscape, a geography of space-time itself. The great physicist Albert Einstein helped us to see that massive objects do not just exist in space, they shape it. They create curves and dips in the very fabric of the cosmos. Imagine a vast, flat, flexible sheet, stretched out tight. This represents the flat space-time of empty space. Now, if you place a heavy ball in the center of that sheet, it will create a depression, a dip in the fabric. This is what the sun does to space-time. It creates a vast, deep depression that we call a gravity well. The planets, including our Earth, are like smaller marbles rolling along the curved edge of this great depression, held in their orbits by its shape. But the Earth, too, has mass, and so it creates its own, smaller depression in the fabric of space-time. It has its own gravity well. It is a much gentler and shallower slope than the Sun's, but it is our local gravitational landscape. As our comet approaches the Earth, it begins to feel the influence of this local curvature. It is no longer just following the grand slope toward the Sun. It is now being drawn into the smaller, more intimate depression created by our own planet. Its trajectory begins to curve more sharply, no longer dictated just by the Sun, but now dominated by the Earth's gravity. It has been captured. It is falling now, not just toward the sun, but down the gentle slope of Earth's gravity well. This is a serene and peaceful image. There is no struggle, no violent capture. It is simply a traveler following the natural contours of the universe, a path laid out for it by the mass of our world. Understanding this invisible landscape, this gentle, curving well in space-time, is the first step to understanding the comet's final, silent approach to our atmospheric doorstep. The journey from being a passing visitor to an inevitable impactor is a matter of incredible precision. The path of our comet must be threaded through an impossibly small, invisible target in space. This target is known to planetary scientists as a gravitational keyhole. Let us imagine the space around our Earth. As objects fly past, their trajectories are bent by our planet's gravity. Most objects are simply deflected, their paths curved slightly as they pass by, before they continue on their journey through the solar system. Their new path is different from their old one, but they do not impact. However, there are tiny specific regions in space, like invisible corridors, that lead to a different outcome. If an object's trajectory happens to pass through one of these corridors, its path will be bent in such a precise way that it is guaranteed to return and impact the Earth on a future pass, or, in our case, to be guided directly into the planet on its current one. This is the gravitational keyhole. It is not a physical object, but a mathematical reality, a region of space-time where the gravitational influence of the Earth is perfectly aligned to ensure a collision. The size of this keyhole is incredibly small compared to the vastness of space. For an object like our comet, it might be only a few hundred miles across. Threading this cosmic needle is an event of incredibly low probability, which is why major impacts are so rare. In our hypothetical story, the gentle nudge that the comet received from the passing asteroid did just this. It minutely adjusted its trajectory so that its path was aligned perfectly with one of these gravitational keyholes. As the comet passed through this invisible gate, its fate was sealed. The laws of physics, in their quiet, impersonal elegance, had determined the outcome. From this moment on, there was no longer any chance of a near miss. The comet was now on a ballistic trajectory, a final, graceful fall down the gravity well, guided by an unseen architect toward the upper layers of our world's atmosphere. This concept of a keyhole path transforms the idea of an impact from a random accident into a beautiful, albeit sobering example of celestial precision. In the final hours of its long journey, our comet is now entirely in the embrace of Earth's gravity. Its great orbital path around the sun is now just a memory. Its motion is a simple, direct, and accelerating fall toward the surface of our planet. The experience from the comet's perspective would be one of profound silence. It is still in the vacuum of space, and the Earth is growing ever larger in its field of view, a beautiful, silent marble of blue, white, and green. Its velocity, which was already immense from its fall toward the sun, now increases even more as it plunges deeper into Earth's gravity well. It is accelerating every second, its kinetic energy building to an almost unimaginable level. This energy, the energy of motion, is the key to everything that is about to happen. It is the inheritance of its long journey from the Oort cloud, a vast store of cosmic momentum that it is now carrying to our doorstep. There is no sound, no sense of rush, just a silent, inexorable closing of the distance. The sun is now at its back, illuminating the planet before it. The intricate patterns of clouds, the deep blue of the oceans, the familiar shapes of the continents, all would become clearer with each passing minute. This is the final, serene moment of its existence as a celestial body. It is the quiet prelude to its interaction with our planet's atmosphere, a transition from a traveler in the void to a participant in the dynamic systems of Earth. This peaceful, final approach sets the stage for the next phase of its journey, a fiery transformation that is about to begin. In our story, we imagined our comet to have a core resilient enough to survive the sun's tidal forces, but the forces it is about to encounter are of a completely different nature. As the comet touches the upper atmosphere, it will be subjected to immense aerodynamic pressure, a force far greater than the gentle tidal pull of the sun. Even our stronger, hypothetical nucleus is, at its heart, still a fragile rubble pile. It is not built to withstand this kind of stress, and so we reintroduce the idea of fragmentation, but this time it happens not in the slow, graceful manner of its real-world counterpart, but in a rapid, cascading collapse. As the comet plunges deeper into the atmosphere, the pressure of the air building up in front of it becomes overwhelming. The nucleus, which has held together for thousands of years, now yields. It will not be a single, monolithic object that strikes the Earth. Instead, in the final minutes of its descent, it will break apart into a cluster of large fragments. Imagine the single body fracturing into a dozen, or perhaps several dozen, significant pieces. These pieces will no longer be traveling as a single point, but as a shotgun blast, a swarm of massive objects all heading for the same general area of the planet's surface. This is a crucial detail in our worst-case scenario. A single, solid impactor would deliver all of its energy to one specific point, but a fragmented impactor will distribute that energy over a much wider area. This cascading fragmentation is not a sign of weakness, but a natural consequence of a cometary body interacting with a dense atmosphere. The comet's structure is simply overwhelmed. The event would be spectacular, a series of flashes and flares in the upper atmosphere as the new fragments are created. This swarm of celestial debris, each piece a mountain of ice and rock, is now on the final, fiery stage of its journey, and our perspective now shifts to that of the Earth itself, watching this silent approach from below. Let us for a moment take a different perspective. Let us imagine ourselves not on the Earth, but with the approaching fragments, looking back at the world they are about to meet. From this vantage point, in the silent, cold vacuum of space, the Earth is a vision of serene and silent beauty. It is a perfect sphere, hanging in the blackness, adorned with swirling patterns of white clouds, the deep, rich blue of the oceans, and the subtle, earthy tones of the continents. As the fragments draw closer, this silent marble grows, filling more and more of the sky. There is no sense of malice or intent in this approach. The fragments are not invaders. They are simply objects following the unchangeable laws of physics. They are pieces of primordial matter, born in the same solar nebula as the Earth itself, now returning after a journey of billions of years. From this detached cosmic perspective, the impending event is not a catastrophe, but a form of cosmic reunion. The side of the Earth facing the fragments is bathed in sunlight. The planet appears as a brilliant, full circle of light. There are no visible signs of the life that flourishes on its surface. The cities, the forests, the myriad creatures that call it home are all invisible, hidden beneath the thin, delicate veil of the atmosphere. The planet appears as a pure, geological object, a physical body in space. This perspective is important because it helps us to maintain the calm, observational tone of our journey. We are not witnessing an attack, but a physical process, an interaction between two celestial bodies. The Earth, in its silent, patient turning, is about to receive a visitor from the depths of the solar system. Holding this peaceful, detached image in our minds, allows us to move into the next phase of our story, the fiery passage through the atmosphere, not with fear, but with a sense of quiet awe for the immense physical forces that are about to be unleashed. The silent, beautiful Earth waits, unaware of the ancient messenger that is about to arrive. As we conclude this chapter, we pause to reflect on the forces that have brought us to this moment. The entire journey of our hypothetical comet, from its gentle nudge in the Oort cloud to its final, inexorable fall toward Earth, has been governed by a simple and elegant set of physical laws. There is a deep and profound serenity in this understanding. The universe is not a chaotic or random place. It operates according to principles that are consistent, predictable, and beautiful in their impartiality. Gravity, the great architect of the cosmos, shaped the comet's path. It was gravity that pulled it from its ancient home, gravity that guided it on a sweeping arc through the solar system, and gravity that bent its trajectory through the invisible keyhole that sealed its fate. The laws of motion dictated its ever-increasing velocity, the silent accumulation of the immense kinetic energy it is now about to deliver. This is a universe of unfolding laws. The events we are imagining are not born of intention or will, but are simply the natural consequence of matter and energy interacting over vast scales of time and space. The comet is not an enemy. The Earth is not a victim. They are two participants in a cosmic dance that has been playing out since the beginning of time. This perspective allows us to approach the next chapter not with apprehension, but with a sense of calm reverence. We are about to witness a demonstration of the conversion of energy on a planetary scale. It is a moment of profound physical transformation. By understanding that we are simply watching the universe follow its own serene and immutable rules, we can observe the coming events with a sense of peaceful wonder, appreciating the immense and beautiful power that is woven into the very fabric of existence. Our traveler has arrived. The silent journey through the vacuum is over, and a new, fiery and transformative chapter begins. We will now follow the fragments as they meet Earth's atmosphere, a protective embrace that will change everything. The boundary between space and our world is not a hard line. It is a slow, gradual transition, a deepening of emptiness into substance. The first tendrils of Earth's atmosphere extend hundreds of miles above the surface, a region known as the exosphere. Here, the air is so incredibly thin that molecules can travel for miles without bumping into one another. For our approaching cometary fragments, this is the first gentle touch of the world they are about to meet. Traveling at tens of miles per second, the fragments plunge into this ethereal outer layer. At first, almost nothing happens. The encounter is too gentle, the air too sparse to have any significant effect. But as they descend deeper into the thermosphere, the density of the air, while still thinner than any vacuum we can create on Earth, begins to increase. The fragments are now encountering more and more air molecules every second. This is the true threshold crossing. This is where the process of atmospheric entry begins. It starts not with a roar, but with a whisper of interaction. The individual atoms on the leading edge of the cometary fragments begin to collide with the atoms of nitrogen and oxygen in the upper atmosphere. Each of these microscopic collisions transfers a tiny amount of energy, but there are trillions upon trillions of them happening every moment. The effect is not friction in the way we normally think of it. It is about compression. The immense speed of the fragments does not give the air in front of them time to move out of the way. Instead, the air is compressed almost instantaneously, squeezed into a superheated plasma. This glowing cushion of incandescent gas is what begins to heat the surface of the fragments. The threshold has been crossed. The cold, dark ice and rock that have traveled for billions of years in the frozen void are now beginning to feel the heat of their arrival. This gentle initial contact is the start of a process that will rapidly intensify, a quiet beginning to a spectacular and fiery transformation. As the fragments descend deeper into the atmosphere, into the mesosphere, the air becomes exponentially denser. The cushion of superheated compressed air in front of them now reaches temperatures of thousands of degrees, hotter than the surface of the sun. This intense heat begins to have a profound effect on the fragments themselves in a process known as ablation. Ablation is the serene and orderly removal of material from a surface through vaporization. The intense heat from the compressed plasma in front of the fragments is transferred to their surfaces. This energy is so immense that it does not melt the ice and rock. It causes them to instantly flash into a gaseous state. The outer layers of the cometary fragments begin to boil away, molecule by molecule. Imagine a block of ice held in the path of an impossibly powerful blowtorch. The surface would not form puddles of water. It would instantly turn into steam. This is ablation. It is a process of controlled, layer-by-layer disintegration. The rock and dust on the surface are vaporized into a glowing gas. The ancient water ice, locked away for eons, is flash-steamed into superheated vapor. The other volatile ices, like carbon dioxide and methane, also turn instantly into gas. This process creates a shroud of vaporized cometary material that flows around the fragments as they fall. This shroud mixes with the superheated atmospheric gases, creating a brilliant, glowing trail in the sky. This is the fiery tail of the meteor, the visible manifestation of the ablation process. It is the comet's own substance being stripped away and painted across the sky. Ablation is also a form of protection, in a way. The process of vaporizing the material consumes an enormous amount of energy. This means that a significant portion of the heat generated by atmospheric entry goes into the process of ablation itself, rather than into heating the core of the fragments. The outer layers are sacrificed to protect the interior. However, the energy of this entry is so great, and the fragments so fragile, that ablation is also a key part of their destruction. They are shedding their mass at an incredible rate, shrinking and being consumed by their fiery passage. It is a beautiful, self-destructive process, a physical transformation that creates a luminous and unforgettable spectacle in the sky. For a hypothetical observer on the ground, watching the night sky, the arrival of the fragments would be a spectacle of profound and silent beauty. There would be no sound at first, as the events are unfolding 60 to 70 miles up in the atmosphere, where the air is too thin to carry sound to the surface effectively. The first sign would be a sudden, new star in the sky, a point of light that quickly grows in brilliance. Then, as the initial fragment begins to break apart in the cascade we imagined earlier, that single point would blossom into a multitude of lights. It would not be an explosion in the traditional sense, but a silent, luminous flowering. The cluster of fragments, each now undergoing its own process of ablation, would appear as a great, expanding flower of fire in the sky. Its petals would be the glowing trails of superheated gas, painting streaks of brilliant color against the dark canvas of the night. The colors themselves would be a beautiful and informative part of the display. The intense heat would cause the different chemical elements in the atmosphere and in the comet to glow in their own signature hues. The nitrogen and oxygen of our own atmosphere would glow with reds and greens, similar to the aurora borealis. The elements within the comet would add their own colors to the palette. Sodium, a common element in cometary dust, would create a brilliant orange-yellow. Iron and nickel would add hints of blue and green. The result would be a celestial firework display of unimaginable scale and beauty, a silent, luminous blossom unfolding high above the world. This silent spectacle would be visible for hundreds, perhaps even thousands of miles around. It would be a moment of shared, silent awe for anyone who happened to be looking at the sky. It is the visual representation of the immense energy conversion that is taking place, a beautiful and serene display that precedes the arrival of the other, more powerful effects of the atmospheric entry. This blossom of light is the first part of the comet's energy that reaches us, a gentle and beautiful harbinger of the immense forces that are at play. As the cometary fragments plummet through the atmosphere at a speed many times faster than the speed of sound, they create a phenomenon of immense power and beautiful simplicity, a shock wave. To understand this, let us use a gentle analogy. Imagine a boat moving slowly through calm water. The water has plenty of time to move out of the way, and it creates gentle waves or ripples that spread out from the bow. Now, imagine that same boat moving at an incredible speed. The water no longer has time to part gently. The boat forces the water aside so quickly that it piles up in front of the bow, creating a sharp, distinct wave. This is the boat's wake. A shock wave is the atmospheric equivalent of this wake. The cometary fragments are moving so fast that the air molecules in front of them cannot flow out of the way in a smooth, orderly fashion. Instead, the fragments act like a piston, compressing the air in front of them almost instantaneously. This creates a sharp, incredibly abrupt boundary in the air. On one side of this boundary is the normal, undisturbed atmosphere. On the other side is a region of incredibly high pressure, density, and temperature. This boundary is the shock wave, or more precisely, a bow shock, as it forms in front of the descending objects. The shock wave itself is invisible, but it is a region of immense energy. It is the primary mechanism that heats the air to incandescent temperatures, causing the glowing plasma that then leads to ablation. The shock wave is attached to the fragments, traveling with them on their downward journey. It is a silent, invisible bubble of extreme pressure, a physical consequence of moving through a medium faster than information can travel through that medium. The formation of this shock wave is not a violent or chaotic process. It is a serene and predictable consequence of hypersonic travel. It is the atmosphere's natural response to the passage of such a fast-moving object. This invisible shield of pressure is where the majority of the comet's kinetic energy will begin its transformation into other forms, like heat and light. The quiet, orderly formation of this shock wave is a crucial step in the process, as it is the vehicle that will eventually carry a significant portion of the comet's energy down to the surface of the planet. The journey continues downward, through the atmospheric layer known as the mesosphere. This region, roughly 30 to 50 miles above the surface, is a realm of increasing density and pressure. For the descending fragments, this is the region of maximum stress, the trial by fire. As they plunge deeper into the mesosphere, the air becomes thick enough to exert a tremendous braking force. The fragments begin to decelerate for the first time, their immense velocity starting to be checked by the resistance of the atmosphere. This deceleration is another form of energy conversion. The kinetic energy that is lost is transformed directly into more heat, making the shock wave even more intense and the process of ablation even more violent. The fragments are now glowing at their absolute brightest, a cascade of brilliant fireballs lighting up the sky. The stresses on them are at their peak. The combination of the intense heat on their surfaces and the crushing aerodynamic pressure is almost unimaginable. Any of the larger fragments that had survived the initial breakup might now be fracturing further, creating yet more smaller pieces in the fiery trail. This passage through the mesosphere is the climax of the atmospheric entry phase. It is the moment of greatest spectacle and greatest destruction for the fragments themselves. They are being consumed, slowed, and broken apart by our planet's protective atmospheric blanket. They are paying a heavy price for their entry. This intense but brief passage through this middle layer of our atmosphere is the final step before the ultimate release of their energy, an event that will happen not on the ground, but high above it. The fragments of our hypothetical comet will never reach the ground. Because they are structurally weak, even in our more resilient scenario, they cannot survive the full journey through the atmosphere. At some point in their descent, likely in the lower mesosphere or the stratosphere, they will reach their breaking point. The aerodynamic pressure acting on them will finally exceed the minimal structural integrity that holds them together. The result is an airburst. An airburst is not a chemical explosion like a bomb. It is a physical disintegration, a catastrophic and near-instantaneous release of energy. The fragments, which have been decelerating and accumulating immense stress, essentially pancake and shatter, exposing all of their remaining mass to the full force of the shockwave at once. All of the fragments' immense kinetic energy is converted into heat and light in a single, brilliant flash. Imagine a dam holding back a vast lake. The airburst is the moment the dam instantly vanishes. All the energy that was stored up is released in a single, overwhelming wave. Each of the dozens of large cometary fragments will undergo its own airburst, creating a series of these titanic energy releases at altitudes of perhaps 10 to 20 miles above the surface. This is the most crucial aspect of our worst-case scenario involving a fragile, fragmented impactor. The danger is not from a crater, but from the energy released in the atmosphere. The airburst phenomenon is what transforms the kinetic energy of the comet's motion into the thermal and blast energy that will affect the surface below. It is the final, spectacular act of the comet's long story. It is a moment of complete and utter transformation, where solid matter from the dawn of the solar system is converted into a blinding flash of light and a powerful wave of pressure high in the peaceful, silent stratosphere. This is the serene climax of its arrival and the beginning of its effects upon our world. The comet's journey through the atmosphere has reached its gentle yet powerful conclusion. Now we will calmly observe the consequence of that final transformation as the energy from the airbursts begins its own silent journey down to the surface of our world. At the heart of the airburst phenomenon is a beautiful and simple principle of physics, the conservation of energy. Energy cannot be created or destroyed, it can only change its form. The comet fragments, as they descended through the atmosphere, possessed an almost unimaginable amount of kinetic energy, the energy of motion. This energy was the sum total of their long, slow fall from the outer edges of the solar system, accumulated over thousands of years. It was a vast inheritance of gravitational potential energy, converted into the currency of speed. The purpose of the atmospheric entry and the airburst was to convert this kinetic energy into other forms. As the fragments were slowed by the atmosphere, some of that kinetic energy was transformed into the heat that created the glowing plasma and drove the process of ablation. But the majority of it was stored for a brief moment in the compressed shockwave. The airburst is the moment when all of the remaining kinetic energy is released in a single, silent, and instantaneous event. It is converted, with incredible efficiency, into thermal energy, heat and light, and the energy of pressure, the shock wave itself. Let us try to gently grasp the scale of this energy release. A single, large cometary fragment, perhaps a few hundred meters across, would release more energy in its airburst than the entire nuclear arsenal of our world. Now imagine a cascade of these events, a dozen or more, all occurring within a few seconds of each other, across a wide swath of the sky. The total energy release is truly astronomical, a force of nature on a planetary scale. But it is crucial to remember that this is not a chaotic or violent release. It is an orderly and predictable transformation, governed by the laws of thermodynamics and fluid dynamics. The kinetic energy of a solid body moving in a straight line is transformed into the radiant energy of photons traveling out in all directions, and the mechanical energy of a pressure wave expanding through the air. There is a serene elegance to this conversion. It is the universe balancing its books, ensuring that the energy that arrived with the comet is perfectly accounted for, as it is distributed into the Earth's atmosphere. Understanding this fundamental process of energy conversion is the key to understanding all of the effects that will now, gently and quietly, begin to unfold below. The first form of energy to reach the surface from the cascade of airbursts is light. In the instant of the airburst, a massive portion of the comet's kinetic energy is converted into a brilliant flash of thermal radiation. For a few brief seconds, a new sun, or rather a series of new suns, would bloom in the sky. This thermal pulse would be a wave of incredible, silent light. From a safe narrative distance, we can imagine its effects with calm observation. For an area of hundreds of square miles directly beneath the airbursts, the intensity of the light would be brighter than the midday sun. The sky itself would appear to catch fire, illuminated by a light of impossible brilliance. Every surface on the ground would be cast into sharp, stark relief, and then be bathed in an overwhelming radiance. This is not the gentle, life-giving light of our own sun, which is filtered and softened by its long journey through space and our atmosphere. This is raw, unfiltered thermal radiation, a direct and powerful wave of electromagnetic energy. It travels at the speed of light, so its arrival on the surface is almost instantaneous with the airbursts themselves. There is no warning, just a sudden, silent, and all-encompassing flash. The energy carried by this light is immense. It is a wave of heat as much as it is a wave of light. Surfaces exposed to the flash would be instantly superheated. The dominant feeling would be one of intense, radiant warmth, as if standing impossibly close to a colossal fire. This thermal pulse is a direct consequence of the airburst's high temperatures. It is the atmosphere itself, heated to millions of degrees in the shockwave, releasing that energy in the most efficient way possible, as a blinding flash of light. This silent arrival of a new, temporary sun is the first major effect of the impact, a serene yet powerful announcement that the comet's energy has now reached our world. Long after the silent flash of light has faded, another form of energy will arrive, traveling at a much more leisurely pace. This is the sound of the airbursts. Sound travels through the air at a relatively slow speed, about 760 miles per hour at sea level. Since the airbursts occurred 10 to 20 miles up in the atmosphere, it would take a minute or more for the sound of those events to travel down to the surface. The sound that arrives would not be a sharp crack or a loud bang. The event that created it was too large, its frequency too low for the human ear to perceive as a typical explosion. Instead, it would be a sound that is felt as much as it is heard. It would begin as a deep, continuous and ominous rumble, like the sound of a distant, impossibly large thunderstorm. This is the sound of the atmosphere itself being torn apart and reformed by the passage of the shockwave. The ground would begin to vibrate gently, a deep, resonant hum that seems to come from everywhere at once. The air would feel thick and heavy with the pressure of these low-frequency sound waves. As the main shockwave arrives, this deep rumble would swell into a deafening, continuous roar, a sound that would overwhelm the senses. It would be less like a single event, and more like the arrival of a great, roaring wind, a physical presence in the air. There is a serene and powerful quality to this deep, rumbling sound. It is the sound of pure, raw energy being released on a planetary scale. It connects the silent, beautiful event in the upper atmosphere to a tangible, physical experience on the ground. Like the low, powerful notes of a great organ, the sound of the air bursts is a testament to the immense scale of the forces at play. It is the atmosphere's voice, finally announcing the arrival of the visitor it had just consumed, accompanying the deep, rumbling sound, and in fact causing it, is the shock wave itself, now traveling through the denser air of the lower atmosphere. As it spreads out from the site of the multiple air bursts, it is no longer a sharp, hypersonic bow shock. It has transformed into a broader, less defined blast wave, which scientists refer to as an overpressure wave. Imagine the normal, ambient pressure of the air around you. The overpressure wave is a momentary, but very powerful increase in that pressure. It is like a sudden, invisible wall of air moving across the landscape. As this wave passes, it is followed immediately by a period of underpressure, where the air pressure drops below normal, creating a powerful, outward rushing wind. From our calm, observational perspective, we can understand this purely as a physical process. The energy that was released in the airburst is being carried through the medium of the atmosphere. The wave is a disturbance, a ripple of pressure expanding outward in a great circle from the point of the explosion. The effects of this overpressure wave are a direct function of its strength. Close to the impact point, the pressure would be immense, a powerful, crushing force. Farther away, it would be experienced as a strong, sudden gust of wind, followed by a strange, momentary calm. This wave of air pressure is the primary mechanical effect of the airburst. It is the mechanism by which the energy of the comet's motion is transformed into a physical force that can interact with the surface of the planet. It is a quiet, invisible, and yet profoundly powerful consequence of the event, a final exhalation of the atmosphere after it has absorbed and transformed the ancient messenger from space. With the passage of the overpressure wave, the atmospheric part of our story comes to a close. We have witnessed the serene conversion of kinetic energy into a brilliant flash of light, a deep, rumbling sound, and a powerful wave of air pressure. The vast majority of the comet's substance and energy has been deposited high in the atmosphere, absorbed by our planet's protective shield. The airbursts have acted as a great brake, preventing a catastrophic impact on the solid ground. However, the journey is not entirely over. While most of the comet was vaporized, it is likely that some of the densest, most resilient fragments from the core of the original nucleus survived the fiery descent. These smaller pieces, perhaps the size of cars or small buildings, would have been slowed dramatically by the atmosphere, but not entirely consumed. They are now continuing their journey to the surface, no longer as brilliant fireballs, but as dark, cold rocks in the final stage of their fall. Their journey is almost complete. We now gently guide our focus downward, away from the spectacle in the sky, and toward the vast, peaceful surface of the ocean, where these last few messengers are about to complete their millennia-long voyage. The final act of our impact scenario is about to take place, not in a blaze of glory, but with a quiet splash in the deep blue water. The fiery spectacle in the sky has passed. Now, the final remnants of our celestial visitor complete their journey, not to the land, but to the vast, forgiving expanse of the open ocean. This chapter is about the planet's ability to absorb such an event, and the quiet, powerful ways it responds. To explore the next phase of our hypothetical scenario in the most serene way possible, we will imagine that the surviving fragments are destined to land in the largest and most empty place on the surface of our planet, the middle of the Pacific Ocean. This choice is a gentle one, By placing the impact far from any coastline, far from any human presence, we can focus entirely on the pure, physical interaction between the celestial objects and the planet itself. The Pacific Ocean is a realm of immense scale and quiet power. It is a body of water so vast that all the continents of the world could fit within its basin. Its average depth is over 2 miles, a colossal cushion of water that makes up nearly half of the world's free water. It is a place of deep silence, of slow, powerful currents, and of a profound, patient rhythm that has been undisturbed for millennia. This is the setting for the final act of our comet's journey. The ocean, in its immense and tranquil majesty, is waiting to receive these last few travelers. There is no sense of fear or hostility in this meeting. It is simply one part of the planet, the hydrosphere, responding to an event from the cosmos. The vast, empty expanse of the Pacific provides a perfect, peaceful theater in which to observe the next beautiful and powerful transformation of the comet's energy. Let us now zoom in on this quiet, sunlit patch of the deep ocean and witness the moment of arrival. The surviving fragments, now dark, cold pieces of rock and ice, fall the last few miles through the lower atmosphere in silence. They hit the surface of the ocean not as a single, coordinated strike, but as a scattered shower, peppering a wide area of the sea. The moment of contact is a beautiful and complex event. As each fragment, traveling at hundreds of miles per hour, strikes the water, it transfers its remaining kinetic energy to the ocean with incredible speed and efficiency. The water, for a brief instant, behaves not like a liquid, but like a solid. The impact creates a brilliant splash, a towering crown of white water and spray that leaps hundreds of feet into the air. But the more profound event happens beneath the surface. The fragment penetrates deep into the water, and the immense heat of the rock and the pressure of the impact instantly flashboil a huge volume of seawater. This creates a vast, expanding bubble of superheated steam. This steam bubble is what drives the creation of a deep, transient crater in the ocean's surface. For a few moments, a great cavity, perhaps miles across, is carved out of the sea. The walls of this watery crater are steep and unstable, and the ocean floor itself may be visible for a fleeting second. Simultaneously, the immense volume of steam, mixed with the vaporized remains of the cometary fragment, erupts back out of the cavity, creating a colossal geyser of hot gas and water that rockets high into the atmosphere. This is the ocean's immediate energetic response to the impact. It is a moment of intense, localized activity in an otherwise tranquil sea. It is a violent and beautiful process, a meeting of cosmic ice and terrestrial water that sets in motion the next, much larger and slower response from the ocean. The creation of the cavity in the ocean is a beautiful example of fluid dynamics on a massive scale. This transient crater, as scientists call it, is a temporary feature, a momentary scar on the sea's surface that tells the story of the energy that has just been deposited. Let us gently explore the serene, wave-like physics of how this crater forms and then heals itself. The initial impact, as we have seen, pushes the water down and away, forming the deep cavity. This is the first phase. The crater reaches its maximum depth and diameter in just a matter of seconds. But water is not a solid. It is a fluid, and it is under the constant pressure of gravity, which is always trying to pull it back to a level state. The steep, unstable walls of the watery crater immediately begin to collapse inward. This inward rush of water is the second phase. Water from all sides flows back toward the center of the cavity, driven by gravity. It rushes down the steep slopes and collides with incredible force at the very center of the impact point. This collision is so powerful that it has nowhere to go but up. This leads to the third and most spectacular phase, the rebound. The colliding water creates a massive central peak, a towering jet of water that can soar thousands of feet into the air, much higher than the initial splash. This is a phenomenon we can see on a small scale when a single drop of water falls into a still pond. After the initial splash and crater, a small, beautiful jet of water rebounds from the center. The impact of a comet fragment is simply this same process on an unimaginable scale. Finally, this towering central peak, itself unstable, collapses back down under its own weight. This final collapse is what sends out the first in a series of powerful, circular waves across the ocean's surface. The entire process, from impact to final collapse, might take only a few minutes. It is a rapid, oscillating, wave-like motion, a beautiful dance of pressure and gravity as the ocean absorbs the impactor's energy and transforms it into the organized, propagating energy of a wave. The ocean has now healed its momentary wound, and in doing so has given birth to a new phenomenon that will travel far beyond the impact site. At the very heart of the impact and the crater formation is a fundamental principle: the transfer of momentum. Momentum is a measure of an object's mass in motion. Our cometary fragments, even after being slowed by the atmosphere, still possessed an enormous amount of momentum due to their high mass and velocity. When they struck the ocean, this momentum had to go somewhere. The fragments came to a very abrupt stop, transferring nearly all of their forward momentum to the water. This is what pushed the water down and out to create the transient crater. It was a massive, instantaneous push on the ocean. But the energy did not simply dissipate in the turbulence of the splash and the creation of steam. A significant portion of it was transferred into a more organized and lasting form of motion. As the crater collapsed and the central peak rebounded, the energy was converted from a localized downward punch into a vast, expanding, circular motion. This is the birth of the tsunami wave. The energy of the falling comet has now been transformed into the potential energy of a massive volume of water that has been lifted above the average sea level, and the kinetic energy of that water as it begins to move outward. This transfer of momentum is incredibly efficient in water. The ocean is an excellent medium for carrying energy over vast distances. Unlike the energy of the airburst, which dissipates relatively quickly in the atmosphere, the energy imparted to the ocean will be carried for thousands of miles with very little loss. The impact was a single point in space and time, but the energy from that impact has now been encoded into the very fabric of the ocean, ready to begin a long and silent journey across the entire Pacific Basin. The initial violent transfer of momentum is now complete, giving way to the quiet and powerful propagation of a newly formed wave. From the chaotic, turbulent center of the impact, a new form of order emerges. A wave. But this is not a wave in the ordinary sense, not like the wind-driven waves that break upon a beach. A tsunami wave born from an impact is a fundamentally different kind of entity. In the deep, open ocean where our impact occurred, the wave is almost unnoticeable on the surface. It is not a towering wall of water. Instead, it is a very long, low swell, perhaps only a few feet high. What makes it so different and so powerful is its wavelength, the distance from one crest to the next. For a wind-driven wave, the wavelength might be a few hundred feet. For a tsunami, the wavelength can be enormous, often over 100 miles long. This means that the wave is not just a surface feature. It is a pulse of energy that extends through the entire depth of the ocean, from the surface all the way down to the seabed, miles below. As this long, low swell begins to propagate outward from the impact site, it travels at an incredible speed. The speed of a tsunami in the deep ocean is not determined by the wind, but by the depth of the water. In the vast abyssal plains of the Pacific, the wave would travel at speeds of over 500 miles per hour, the speed of a modern jetliner. So let us hold this serene image in our minds. A series of very long, very low, very fast waves, radiating outward in perfect circles from the point of impact. On the surface, a ship passing over it would barely notice a gentle rise and fall of the sea. But beneath the surface, a colossal amount of energy is being transported in perfect silence across the ocean basin. This is the birth of the wave, a quiet, powerful, and incredibly swift messenger, carrying the story of the comet's impact far and wide. The initial chaos of the event has settled, and the planet's long-term response now begins its journey. Back at the site of the impact, a profound calm begins to return. The great geysers of steam have dissipated, the towering central peak has collapsed, and the transient crater has vanished as if it never existed. The surface of the ocean, which was for a few minutes a scene of unimaginable turmoil, is now settling back into its familiar, rhythmic swell. The only immediate signs of the event might be a large patch of steamy, turbulent water, perhaps warmer than the surrounding sea. There might be some floating debris, a thin slick of strange, extraterrestrial dust and minerals on the surface. But the ocean's immense capacity to absorb and dissipate energy means that even these signs will quickly fade. The currents will carry the debris away, and the warmth will be lost to the vast thermal mass of the water. Within hours, the site of the impact would be indistinguishable from any other patch of the open ocean. The sky above is clear, the sun shines on the water's surface, and the deep, silent world below returns to its timeless state. The ocean has done its work. It has accepted the last remnants of the cosmic visitor, absorbed the immediate shock of their arrival, and transformed their energy into a form that it can carry away. This image of the ocean settling provides a moment of peaceful closure to the impact event itself. The comet's long journey is now truly, finally over. Its substance has been scattered in the atmosphere and dissolved in the sea. But its legacy, its energy, lives on, encoded now in the silent, powerful waves that are at this very moment racing across the Pacific. Our story now leaves the point of impact behind and follows these ripples of change on their great global journey. The direct, dramatic events of the impact are over. Now we enter a phase of quiet, planetary consequences. This chapter is about the slow, silent, and far-reaching effects of the energy that has been delivered to our world as they spread across the globe. The tsunami wave, born in the turbulent aftermath of the ocean impact, now begins its great journey. It is a messenger of pure energy, traveling silently across the vast, deep basin of the Pacific Ocean. As we learned, in the open ocean, it is a subtle and almost imperceptible phenomenon. A series of long, low swells, perhaps only a foot or two in height, but with hundreds of miles separating one crest from the next. Its speed is almost beyond comprehension. At 500 miles per hour, it would cross the entire Pacific, from Asia to the Americas, in less than a day. This is a journey of thousands of miles, accomplished in profound silence. There is no sound associated with the wave's passage in the deep ocean, no visible sign of the immense power it carries. The energy is contained within the entire water column, a moving pulse that stretches from the sunlit surface to the dark, cold abyss of the ocean floor. As this silent swell travels, it passes over the great, unseen geography of the seabed. It moves over vast, flat plains, over the towering peaks of underwater volcanoes, and across the deep trenches that mark the boundaries of the Earth's tectonic plates. The shape of this seabed has a subtle influence on the wave, gently refracting and steering it. But in the deep water, its energy remains coherent and powerful. This is a beautiful and serene image to hold in our minds. A wave that is as fast as a jet, as long as a country, but as low as a gentle swell. It is the planet's circulatory system at work, transporting the energy from a single point of impact across an entire hemisphere. The journey of this silent swell is a testament to the interconnectedness of our world's oceans, a demonstration of how a single event in one remote location can send a physical signal to the farthest corners of the globe. This quiet, swift journey across the deep basin is the prelude to the wave's dramatic transformation as it finally approaches the distant shore. As the tsunami wave, after its long and swift journey across the deep ocean, finally approaches a distant coastline, it begins to undergo a profound and dramatic transformation. The water is becoming shallower. This change in depth is the trigger for a process known as shoaling, which will convert the low, fast-moving wave into something very different. Let us gently explore the physics of this process. The energy of a tsunami wave, as we know, is distributed throughout the entire depth of the water. In the deep ocean, there is a vast amount of vertical space for this energy to occupy. But as the ocean floor begins to slope upwards, forming the continental shelf, this vertical space begins to shrink. The energy that was once spread out over 2 or 3 miles of depth is now being compressed into a much shallower column of water. This energy has to go somewhere. As the bottom of the wave begins to feel the seabed, it starts to slow down due to friction. The front of the wave is now moving slower than the back of the wave, which is still in deeper water. This causes the wave to compress horizontally, like a spring being squeezed. Its enormous wavelength begins to decrease dramatically. This compression of energy, both vertically and horizontally, has a startling effect on the wave's height. The only place for the energy to go is up. The water begins to pile up on itself. The low, foot-high swell that was almost invisible in the deep ocean begins to grow, rising steadily as the water gets shallower and shallower. By the time it reaches the coast, a wave that was only a couple of feet high in the deep ocean could have grown into a towering wall of water tens, or even hundreds of feet high. This process of shoaling is a beautiful and powerful example of the conservation of energy. The wave's energy is not lost as it comes ashore. It is simply transformed. Its speed decreases, its wavelength shortens, and its height or amplitude increases dramatically. It is a serene and predictable process, governed by the simple relationship between the wave's speed and the water's depth. Understanding shoaling is the key to understanding how a subtle swell in the middle of the ocean can become an event of immense power at the coastline. When the transformed wave finally arrives at a coastline, it may not look like a typical crashing surf wave. A classic tsunami, especially one generated by an impact, is often experienced not as a breaking crest, but as something much more strange and powerful, an inexorable and incredibly rapid rise of the sea itself. Imagine standing on a peaceful, uninhabited shoreline. The first sign might be a strange, quiet withdrawal of the sea as the trough of the long wavelength wave arrives first, pulling the water far out from the shore and exposing the seafloor in a way that is both eerie and unnatural. This is the ocean taking a deep breath before it exhales. Then, the crest of the wave arrives. It appears on the horizon not as a curling breaker, but as a fast-moving, turbulent wall of water. Or, perhaps more commonly, it manifests as an incredibly swift and relentless rise of the tide. The sea level simply begins to climb, rising foot by foot, second by second, with an unstoppable momentum. It surges over the beach, past the high tide line, and continues to move inland. It is not so much a wave as it is a flood, a temporary and sudden reclaiming of the land by the sea. This inexorable rise is driven by the immense volume of water in the wave. Because of its long wavelength, the crest of the tsunami can take many minutes to pass. For all of that time, the sea continues to pour inland, a powerful, debris-filled current that can inundate coastal lowlands for miles. There is a quiet, powerful relentlessness to this process. It is the simple, physical consequence of the energy that was imparted to the ocean thousands of miles away, now finally being released upon the land. In our hypothetical scenario, this event plays out on remote, unpopulated coastlines, a beautiful and powerful demonstration of the planet's raw energy. While the tsunami wave is making its long journey across the ocean, another, much slower and more subtle process is beginning high above in the atmosphere. Let us return our minds to the site of the airbursts. When the cometary fragments disintegrated, they did not simply vanish. They were vaporized into a cloud of incredibly fine dust and gas. The impact with the ocean surface also threw a colossal amount of water vapor high into the stratosphere. This mixture of fine cometary dust and water vapor now begins its own global journey. High in the stratosphere, above the weather systems of our world, are the jet streams, powerful, high-altitude winds that circle the globe. These winds are like great, silent rivers in the sky, and they will pick up this cloud of fine, particulate matter and begin to slowly, gently, and inexorably spread it around the entire planet. This is not a fast process. It will take weeks and then months for the material to be fully distributed. It begins as a localized, high-altitude cloud, invisible from the ground. But as the stratospheric winds do their work, this cloud is stretched and thinned, like a drop of ink in a slowly stirred bowl of water. It spreads east and west, and eventually north and south, until it forms a thin, even, and almost imperceptible veil that covers the entire globe. This veil is composed of microscopic particles of silicate dust from the comet's rocky components and tiny ice crystals formed from the water vapor. It is a new, temporary layer in our planet's upper atmosphere, a subtle, global memento of the comet's fiery arrival. This slow, silent spreading of the atmospheric dust is a process of profound and quiet change, and it will be the source of the most significant and longest-lasting consequence of our entire hypothetical event, a gentle change to the very climate of our world. In the first hours and days following our hypothetical event, for the vast majority of the planet, nothing would seem to have changed. The sun would rise and set as it always does. The weather would follow its familiar patterns. Life would continue its daily rhythms, completely unaware of the immense drama that had just unfolded high in the atmosphere and in a remote patch of the Pacific Ocean. This is a testament to the immense scale and resilience of our planet. The Earth is so large, its system so massive and full of inertia, that even an event of this magnitude is, at first, a purely local phenomenon. The energy of the airbursts and the ocean impact is still contained, either in the expanding tsunami wave or in the slowly spreading cloud of dust in the stratosphere. This initial period of quiet is a gentle reminder of the different timescales on which planetary processes operate. There is the instantaneous timescale of the airburst flash, the minutes-long timescale of the sound and pressure wave, the hours-long timescale of the tsunami's journey, and now the weeks and months-long timescale of the atmospheric and climatic response. We are entering the final and most subtle phase of our story, the one that unfolds not with a flash or a roar, but with a quiet, gradual, and global change. The world seems unchanged for now, but high above, the silent, invisible ripples of the event are spreading, preparing to cast a gentle but persistent shadow over the entire planet. This moment of calm is the quiet before the slow, serene unfolding of a global twilight. The immediate dynamic events have passed. Our story now moves into a phase of quiet, global consequence. We will observe how the fine dust from the comet's demise, now spread throughout the upper atmosphere, begins to gently and subtly change the nature of the sunlight that reaches our world. Weeks have now passed since the fiery arrival of our comet. High in the stratosphere, the fine dust from the airbursts and the ice crystals from the vaporized ocean water have been carried by the silent, powerful jet streams, spreading from a concentrated cloud into a thin, uniform layer that encircles the entire globe. From the surface of the Earth, this change would be almost imperceptible at first. It would not be a dark or ominous cloud, but a very subtle, high-altitude haze. The sky might lose a tiny fraction of its deep, brilliant blue. It might take on a slightly paler, more washed-out quality. On a perfectly clear day, the sun might seem to shine with just a little less intensity, its edges appearing not quite as sharp as they once did. These are subtle clues, things that one might not even notice unless they were paying very close attention. This stratospheric haze is a beautiful and serene phenomenon. It is composed of particles so small that they can remain suspended at that altitude for years, floating high above the weather and the clouds of the lower atmosphere. They are too light to fall quickly back to Earth, and too high to be washed out by rain. They simply drift, a silent, global veil woven from the substance of a visitor from the outer solar system and the water of our own oceans. The formation of this haze is a completely natural process. The Earth has experienced this before, most notably after very large volcanic eruptions, which can also inject massive amounts of fine dust and sulfate aerosols into the stratosphere. The effect is the same: the creation of a persistent, planet-wide layer of fine particles that can gently, but significantly, interact with the sunlight that passes through it. The quiet, almost invisible formation of this spreading haze is the first step in a chain of events that will lead to a gentle but noticeable change in the planet's overall energy balance. The fine veil of dust and ice crystals now suspended in the stratosphere has a simple and direct effect on the sunlight that attempts to pass through it. Each microscopic particle acts like a tiny mirror, reflecting a small amount of sunlight back into space before it has a chance to reach the ground and warm the planet. This phenomenon is known as global dimming. It is not a dramatic or sudden darkening. The effect would be very subtle. Overall, the total amount of solar energy reaching the Earth's surface might be reduced by only a few %. This is not enough to plunge the world into darkness, but it is enough to have a significant and measurable effect on the planet's climate system. The sunlight that does make it through the haze would also be more diffuse, less direct. On the ground, this might be experienced as a world with fewer sharp shadows, a world bathed in a slightly softer, more filtered light. This gentle dimming of the sun is a direct consequence of the laws of optics. The high albedo particles, meaning they are highly reflective, are simply scattering a portion of the incoming solar radiation. It is a serene and impartial physical process. The veil is not intentionally blocking the sun. It is simply there, and its presence alters the path of the light. This reduction in solar energy at the surface is the primary driver of all the climatic effects that will follow. The Earth's climate is, at its heart, a heat engine, driven by the energy it receives from the sun. By gently turning down the flow of that energy, the atmospheric haze has made a subtle but fundamental change to the operating conditions of that engine. The planet will now begin its slow, quiet, and inevitable response to this new reality, a gradual cooling of its surface. While the overall effect of the stratospheric haze is a gentle dimming, it would also create a side effect of breathtaking and serene beauty. Each day, As the sun rises and sets, its light must travel through a much thicker slice of the atmosphere than when it is high in the sky. This light would now also be passing through the new, thin veil of cometary dust. The fine particles in this layer are the perfect size to scatter the blue and green wavelengths of light more effectively, while allowing the red and orange wavelengths to pass through more directly. The result would be a series of sunrises and sunsets of the most spectacular and vivid colors imaginable. The sky would be painted with deep, fiery reds, brilliant oranges, and soft pastel purples that would linger long after the sun had dipped below the horizon. This is the same phenomenon that creates the famously beautiful sunsets that often follow a major volcanic eruption. The dust from the eruption enriches the atmosphere with scattering particles, turning the twilight sky into a magnificent canvas of color. In our hypothetical story, the dust is not from a volcano, but from a comet, but the optical principle is exactly the same. This unintended beauty is a gentle reminder that even in an event born of immense and destructive power, there can be moments of profound and quiet grace. The same veil that is subtly dimming our world and cooling its climate is also gifting it with a daily spectacle of serene and awe-inspiring color. It is a quiet, cosmic paradox, a beautiful silver lining to the subtle gray cloud that now envelops our world. The primary and most significant long-term consequence of the global dimming is a slow, gentle, but globally consistent cooling of the Earth's surface. With less solar energy reaching the ground and the oceans, the planet's overall energy budget is now slightly in deficit. It is radiating slightly more heat back into space than it is receiving from the sun. This imbalance, though small, will inevitably lead to a drop in global average temperatures. This process would be incredibly slow and gradual. It would not be a sudden plunge into a deep freeze. The Earth's oceans, in particular, act as a colossal thermal buffer. They can hold an immense amount of heat, and they would release this heat very slowly, moderating the cooling effect. The initial temperature drop might be almost imperceptible, lost in the noise of normal day-to-day weather variations. But over the course of months, and then a year or two, a clear and steady trend would emerge. Climatologists would begin to notice that average temperatures, when measured across the entire globe, were consistently a little bit lower than they should be. The effect might be a cooling of 1 or 2 degrees Celsius on average. This may not sound like much, but on a global scale, it is a very significant climate shift. It is comparable to the temperature changes seen between mild ice ages and warm interglacial periods, but happening on a much, much faster timescale. This impact winter is a serene and silent process. There are no howling winds or dramatic storms associated with it directly. It is simply a quiet, persistent, and global reduction in the planet's thermal energy. The winters might become slightly longer and colder. The summers might be a little cooler and shorter. Mountain glaciers might advance slightly, and the sea ice in the polar regions might expand. It is a gentle, planetary scale response to the new, veiled reality of the skies, a slow exhalation as the Earth's great heat engine adjusts to a lower power setting. The planet is finding a new, cooler equilibrium, a state of balance it will maintain for as long as the gentle veil of dust remains. The gentle cooling of the planet and the dimming of the sun would, in turn, elicit a quiet and slow response from the Earth's biosphere, the global ecosystem of living things. This would not be a story of sudden catastrophe, but one of slow, patient adaptation and resilience. The first to respond would be the foundation of almost all life on Earth: the plants. With slightly less sunlight and cooler temperatures, the growing seasons in many parts of the world would become shorter. The overall rate of photosynthesis, the process by which plants convert sunlight into energy, would slow down a little. This might manifest as forests that are slightly less lush, grasslands that are a little less verdant. The changes would be subtle, a gentle downshifting of the planet's biological productivity. Animals, in turn, would respond to these changes in the plant life and the climate. Some species might shift their ranges, slowly migrating toward the equator to follow the warmer temperatures. Hibernating animals might begin their winter sleep a little earlier and wake up a little later. The entire rhythm of the natural world would be subtly retuned to this new, cooler reality. The key here is the pace of the change. Because the cooling is gradual, unfolding over a year or two, the biosphere would have time to adjust. This is not a sudden shock to the system. It is a slow, persistent pressure. The story of the biosphere's response would be one of incredible resilience. Life on Earth is adaptable and tenacious. It has survived far greater climate shifts in its long, 4-billion-year history. This gentle, hypothetical cooling would be a challenge, but one that the vast, interconnected web of life would quietly and patiently meet, demonstrating its enduring ability to find a balance in a slowly changing world. The veil of dust and ice in the stratosphere is not a permanent feature. Over the course of several years, the microscopic particles that form it will inevitably fall back to Earth. The process is incredibly slow. Gravity exerts a constant, gentle pull on each particle. Over a period of 3 to 5 years, this subtle tug is enough to pull the vast majority of the material out of the stratosphere and down into the troposphere, the lower layer of the atmosphere where our weather occurs. Once the particles enter the troposphere, they are quickly caught up in the planet's weather cycle. They are absorbed by water droplets in clouds and are gently washed out of the sky by rain and snow. This process is the planet's self-cleaning mechanism. The atmosphere, over time, purifies itself, returning to its former state of clarity. As the stratospheric veil thins and eventually disappears, the amount of sunlight reaching the surface will slowly and gradually return to normal. The global dimming will end. The spectacular sunsets will fade back to their usual, gentle beauty. With the return of the full strength of the sun, the planet's energy budget will shift back into a surplus. The Earth will once again be absorbing more energy than it is radiating, and a new, slow process of gentle warming will begin. The impact winter will come to a close. The planet's climate system, with its immense thermal inertia, will begin the long, slow process of returning to its previous equilibrium. This is not a quick rebound, but a gradual recovery that might take decades or even centuries as the deep oceans slowly warm back up. This long, slow return to normalcy is a testament to the fundamental stability and resilience of our planet's climate, setting the stage for the final healing of our world. The veil has lifted. The gentle winter has passed. Our story now enters its final phase of consequence, a time of quiet recovery and reflection, as the planet's systems return to their timeless equilibrium, leaving behind only the faintest memory of the visitor. Let us imagine ourselves now, several years after the event. The long, slow process of atmospheric cleansing is nearing its completion. The last of the fine cometary dust and ice crystals have been gently pulled from the stratosphere by gravity, falling into the embrace of the weather systems below. They have been washed from the air by 1,000,000 different rain showers, settling unnoticed on the leaves of forests, the surfaces of oceans, and the quiet, sleeping soils of the continents. The sky is returning to its former, brilliant clarity. The deep, familiar blue, which had been subtly muted for years, is now restored. The sun shines with its full, unfiltered strength, its light once again casting sharp, clear shadows upon the land. The gentle, diffuse light of the impact winter has given way to the bright, direct light of a normal era. This clearing of the skies is a profoundly peaceful and hopeful process. It is like a long, slow dawn after a dim and overcast day. The planet is, in essence, taking a deep, cleansing breath. The atmospheric systems, which had been subtly altered by the presence of the dust veil, are now returning to their natural state. The air is once again transparent to the life-giving energy of the sun. This is a visible, tangible sign of the planet's recovery. It is a testament to the powerful, self-correcting mechanisms that are built into the Earth's systems. The atmosphere is not a static entity. It is a dynamic, fluid medium that is constantly in motion, constantly cleansing and renewing itself. The clearing of the skies is the first step in the final healing of the planet, a quiet, beautiful, and definitive end to the global twilight, allowing the climate itself to now begin its own slow journey back to warmth. With the skies now clear and the full energy of the sun once again reaching the surface, the Earth's climate begins its own slow, patient rebound. The gentle cooling trend that dominated the planet for several years has stopped, and a new trend of gradual warming now takes its place. This is the planet's immense climate system seeking its natural equilibrium. The driving force behind this rebound is the oceans. During the impact winter, the surface waters of the ocean cooled, but the deep ocean, with its colossal volume, retained its warmth. The oceans possess what scientists call a high thermal inertia, meaning they are very resistant to changes in temperature. They act as a giant, global thermostat, a memory of the climate that was. Now that the sun's energy is restored, the surface waters begin to warm again, and the deep ocean slowly releases its stored heat, accelerating the process. This is not a rapid warming. Just as the cooling was a slow and gentle process, so too is the recovery. It might take many decades or even a century for the global average temperatures to climb back to their pre-impact levels. The planet's climate has a long memory, and the effects of the cooling will linger in the deep ocean for a long time. On the surface, the changes would be subtle, year by year. The winters would slowly become a little milder, the summers a little warmer. The mountain glaciers that had advanced would begin their slow retreat. The sea ice that had expanded would shrink back to its former extent. It is a slow, generational process of recovery, a quiet and steady return to the climatic norms that are best suited for the life that inhabits the planet. The rebound of the climate is a beautiful demonstration of the Earth's resilience, its powerful tendency to return to a state of life-sustaining balance. As the climate slowly and gently rebounds, so too does the biosphere. The web of life, which had quietly adapted to the cooler, dimmer conditions, now begins to adapt once again to the returning warmth and light. This is a story of life's enduring and profound patience. The plant kingdom leads the way. With warmer temperatures and longer growing seasons, the forests and grasslands begin to recover their former productivity. The subtle decline in growth is reversed, and the planet's green mantle once again becomes more lush and vibrant. This recovery at the base of the food chain sends a ripple of abundance upward. The animal species that may have shifted their ranges begin a slow, multi-generational journey back to their ancestral homes. The natural rhythms of migration, hibernation, and reproduction, which had been subtly altered, now slowly return to their familiar cadence. There is no sense of urgency in this recovery. It unfolds at the pace of nature itself, the pace of changing seasons, and the slow turning of years. The biosphere demonstrates its incredible resilience, its ability to weather the subtle storms of planetary change. The impact winter was a gentle test, and life has passed it with quiet, patient grace. This recovery is a comforting reminder of the deep, powerful, and enduring nature of life on our world. It is a system that is constantly adapting, constantly healing, and constantly persisting, a quiet and beautiful counterpoint to the immense, impersonal forces of the cosmos. While the atmosphere, the climate, and the biosphere all slowly return to their previous state, leaving almost no trace of the event, one part of our planet will hold a permanent memory. Let us return one last time to that remote patch of the Pacific Ocean where the final fragments of the comet came to rest. Here, on the deep, silent floor of the abyss, a subtle scar remains. The hypervelocity impacts of the larger fragments would have been powerful enough to create small, permanent craters in the soft sediment of the seabed. These would not be vast, dramatic structures, but perhaps a series of shallow, bowl-shaped depressions, a few hundred feet or a few miles across. In the utter darkness and stillness of the abyssal plain, these features would be preserved with perfect clarity. Over the coming centuries and millennia, a slow, patient rain of marine sediment would begin to cover these scars. The tiny shells of microscopic sea creatures, fine dust blown from the continents, and the quiet, constant settling of organic matter would gently bury the craters, layer by layer. They would become ghost structures, hidden beneath a blanket of new geological history. But they would still be there. Millions of years in the future, a robotic submarine exploring the seabed, using sonar to map its topography, might detect these strange, circular anomalies. Future geologists, drilling sediment cores in the area, would find a strange, disturbed layer, a moment of chaos frozen in the otherwise orderly record of the deep sea. This subtle scar on the seabed is the planet's most enduring physical memory of the event, a silent, humble monument to the visitor who came from the Oort cloud, a final, quiet testament to a story that has otherwise vanished into time. And so, our hypothetical story of the aftermath comes to its gentle close. We have followed the planet through its quiet winter and into its slow, patient spring. The skies have cleared, the climate is rebounding, and the resilient web of life is healing. The ocean has settled, holding the only permanent physical scar of the event deep within its silent embrace. The world has returned to a state of serene and familiar equilibrium. The comet is gone. Its substance has been scattered and assimilated, its energy absorbed and dissipated. The dramatic events of its arrival, the fiery blossom in the sky, the deep rumble of its passing, the great wave that crossed the ocean, are now just a memory, a story that exists only in our shared imagination. The planet has weathered the encounter, its powerful, self-regulating systems demonstrating their profound and quiet strength. The end of the story's aftermath is a return to normalcy. It is a gentle closing of the circle. The disturbance from the cosmos has been met, absorbed, and healed by the patient and resilient world on which we live. This complete recovery now allows us to take a final step back, to look at how such a profound, yet transient event would be remembered not in the living world, but in the deep, silent memory of the Earth's geology. The story has played out, and the planet has healed. But how would such an event be remembered in the language of the Earth itself? This chapter is a quiet exploration of the subtle, permanent traces that our hypothetical impact would leave behind in the great library of the geological record. We return to the fine, microscopic dust from the comet that was washed out of the atmosphere by the rain and snow. This material, composed of tiny silicate minerals and compounds from a body that formed in the outer solar system, settled everywhere on the planet's surface. It fell as a gentle, invisible rain upon every continent, every ocean, every forest, and every ice sheet. Over the course of a few years, as the atmosphere cleansed itself, this process created a thin, globally consistent layer of extraterrestrial material. This layer would be incredibly thin, perhaps only as thick as a single sheet of paper, or even less. To the naked eye, it would be completely invisible, just another layer of dust settling upon the world. But chemically, it would be unique. It would have a composition subtly different from the normal terrestrial dust that constantly circulates in our atmosphere. This thin stratum is the most important and widespread signature of our hypothetical event, in places where sediments are being deposited in a slow, orderly way, on the bottom of quiet lakes, in the deep sea, or on the great ice sheets of the poles. This layer of cosmic dust would be perfectly preserved. It would become a permanent marker, a geological horizon line, separating the rock and ice laid down before the event from the rock and ice laid down after. This is the Earth's own, quiet way of recording history. It does not write in words, but in layers of stone and ice. This thin, global blanket of dust, a final sprinkling of the comet's own substance, would become a definitive chapter in that great stone book, a silent, permanent echo of the visitor's arrival, waiting patiently to be read by the curious minds of a distant future. In the coldest and most remote places on our planet, in the vast, silent ice sheets of Antarctica and Greenland, the Earth keeps its most perfect and detailed atmospheric archive. Every year, a new layer of snow falls, and over the centuries, this snow is compressed into solid ice. By drilling deep into this ice and extracting long cylinders, known as ice cores, scientists can read the history of the Earth's climate and atmosphere year by year, going back hundreds of thousands of years. In this frozen library, our hypothetical impact event would be recorded with beautiful and serene clarity. Future scientists, drilling a core thousands of years from now, would come to a specific depth and find our thin layer of cometary dust, perfectly preserved between two annual layers of ice. They could analyze this dust, determining its chemical and isotopic composition, and they would immediately recognize it as being of extraterrestrial origin. But the ice cores would tell them even more. Trapped within the ice are tiny bubbles of air, pristine samples of the atmosphere from the year that the snow fell. By analyzing the air in the bubbles just above and below the dust layer, the scientists could reconstruct the atmospheric changes caused by the event. They might see a spike in certain gases associated with the comet or the high-temperature chemistry of the airburst. Furthermore, by analyzing the isotopic composition of the water ice itself, which is a proxy for temperature, they could clearly see the climatic effects of the impact. They would find the sudden, gentle onset of the cooling period, the impact winter, lasting for several years, followed by the long, slow recovery. The ice core would tell the entire story: the arrival of the extraterrestrial material, the immediate atmospheric consequences, and the long-term climatic response. It would be a complete and unambiguous narrative, written in the delicate and beautiful language of frozen water and trapped air, a perfect and silent echo of the event, preserved for all time in the planet's polar regions. Just as the ice sheets keep a record of the atmosphere, the floor of the deep ocean keeps a perfect record of what settles out of the water. On the vast, quiet, abyssal plains, far from the turmoil of the coastlines, sediment accumulates in a slow, patient, and almost perfectly undisturbed sequence. This process, happening over millions of years, creates a layered archive of Earth's history that is in many ways even longer and more complete than the ice cores. Our thin, global layer of cometary dust would have settled through the oceans and come to rest on the seafloor. Here, it would have been gently buried by the continuous, slow rain of marine snow, the shells of plankton, fine clay, and other particles. In the geological record, it would become what is known as a boundary layer, a thin, dark line in a deep-sea sediment core. Future geologists, extracting these cores, would see this line as a clear and definitive punctuation mark in the story of the planet. Below the line would be the fossils of marine organisms that lived before the event. Above the line, they might see a subtle shift in the types of organisms, a record of how the marine ecosystem responded to the gentle cooling of the surface waters. The boundary layer itself would be a treasure trove of information. By analyzing its composition, the scientists could confirm its cosmic origin. They could compare it to the same layer found in other sediment cores from around the world to confirm that the event was truly global in scale. The deep-sea sediments provide a different kind of record than the ice cores. It is less detailed on a year-to-year basis, but it is more robust, capable of preserving the story for tens or even hundreds of millions of years. It is another beautiful example of the planet's quiet, patient bookkeeping, a story written in the fine, silty memory of the deep ocean. Within the thin layer of cosmic dust, there would be a very special and specific clue, a chemical fingerprint that is the unmistakable signature of an extraterrestrial impact. This is an anomalously high concentration of the element iridium. Iridium is what is known as a siderophile, or iron-loving element. When the Earth was young and molten, most of its native iridium sank with the iron to form the planet's core. As a result, iridium is incredibly rare in the Earth's crust. However, asteroids and comets, which are primitive bodies that never underwent this process of differentiation, are relatively rich in iridium. When a large extraterrestrial body impacts the Earth and its material is distributed around the globe, it seeds the surface with this rare element. The result is a thin layer in the geological record that contains hundreds or even thousands of times the normal crustal abundance of iridium. This is known as the iridium anomaly. The most famous example of this is the iridium layer found at the Cretaceous-Paleogene boundary, the geological marker of the impact event that led to the extinction of the dinosaurs 66 million years ago. The discovery of this global iridium anomaly was the key piece of evidence that first led scientists to propose the impact hypothesis. In our hypothetical story, the layer of cometary dust would also be an iridium anomaly. Future scientists analyzing the dust from the ice cores or the deep-sea sediments would find this dramatic spike in iridium concentration. It would be the final, irrefutable proof of what had happened. It would be the unique and unambiguous chemical signature, a calling card left behind by the visitor from the cosmos. This single, simple chemical clue would be the clearest and most powerful echo of the event, a silent testament written in the language of the elements. As we conclude this gentle exploration of the geological record, we are left with a serene and profound idea. The Earth has a memory. It is not a living, conscious memory, but a quiet, physical memory, recorded in the very substance of the planet itself. The layers of ice, the deep-sea sediments, the subtle chemical anomalies, these are the pages of the planet's autobiography. Our hypothetical comet impact, which was such a dramatic and transformative event for the living world in the short term, would eventually fade from all living memory. But it would never be truly forgotten by the planet. It would be a permanent part of its story, a thin, quiet layer in the great library of geological time. The Earth, in its slow, patient turning, acts as the ultimate witness. It observes every major event that occurs on its surface and in its skies, and it keeps a perfect, impartial record. This concept of a planetary memory is a deeply comforting one. It connects us to the immense, deep history of our world. It reminds us that we are living on a planet that has experienced and recorded countless such stories over its long, 4.5 billion-year existence. The quiet memory held in the rock and ice gives us a sense of perspective, a sense of our own small but beautiful place within an ancient and ongoing cosmic story. Our long, hypothetical journey is now coming to a close. We have followed a comet from the edge of the solar system, watched it meet our world, and seen how the planet healed and remembered. Now, we take one final step back to reflect on the quiet, cosmic lessons of our story. Our story may have seemed like a tale of a rare and exceptional event, but in the grander sweep of cosmic time, it is a perfectly normal part of the life of a solar system. The quiet, peaceful sky that we see above us each night is not a static, unchanging backdrop. It is a dynamic and living place, filled with motion, change, and the slow, patient unfolding of physical laws. Comets and asteroids are not intruders in our solar system. They are fundamental and original members of it. They are the leftovers, the ancient building blocks that were never incorporated into planets. Their journeys, which occasionally bring them into the inner solar system, are not aberrations. They are a natural and necessary part of the great celestial dance. These events have been happening since the planets first formed, and they will continue to happen for billions of years to come. In the early days of the solar system, such impacts were far more common, and they played a crucial role in the formation of the planets. It was impacts from comets and asteroids that likely delivered much of the water that now fills our oceans, and the organic compounds that may have been the precursors to life. To look up at the sky is to look into a place of constant, serene change. The planets are moving, the stars are drifting, and countless smaller bodies are following their own ancient orbital paths. Our journey with comet ATLAS was a gentle reminder of this dynamic reality. It helps us to see the solar system not as a fixed and perfect clockwork mechanism, but as a vast, evolving ecosystem. The journey of a comet is not a threat to the natural order. It is an expression of it. This perspective allows us to feel a deeper and more peaceful connection to the cosmos, to see ourselves not as separate from it, but as an integral part of its grand, unending story of change. Throughout our hypothetical story, there has been one silent, constant, and powerful guardian: our planet's atmosphere. It played one of the most crucial roles in our narrative, transforming a potentially catastrophic event into one that the planet could gracefully absorb and heal from. The atmosphere is a gift of profound and quiet importance. Without it, our story would have been very different. The cometary fragments would not have been subjected to ablation and deceleration. There would have been no fiery blossom in the sky, no gentle air bursts to dissipate the energy. The fragments would have struck the surface of our planet with their full, unmitigated cosmic velocity. The result would have been a series of devastating hypervelocity impacts, carving deep, permanent scars into the Earth's crust and releasing a cataclysmic amount of energy directly at the surface. Our moon, which has no atmosphere to protect it, is covered in the scars of such a history. But our planet is different. It is wrapped in this delicate, gaseous blanket, this multi-layered shield that is both transparent to the gentle light of the sun and incredibly effective at protecting us from the kinetic energy of cosmic visitors. In our story, the atmosphere acted as a great planetary-scale brake. It absorbed the immense energy of the comet and spread it out, both in space and in time. It converted the focused, kinetic energy of solid bodies into the diffuse, manageable energy of light, sound, and pressure. To look up at the blue sky is to look at a shield of incredible elegance and power. It is the reason our world is a tranquil haven for life, a place where the violence of the cosmos is tamed and transformed into events of serene, albeit awesome, beauty. Our atmosphere is a quiet, unsung hero, a constant and gentle embrace that makes our living world possible. In our story, the arrival of the comet was a hypothetical surprise. But in our real world, we are not passive observers of the sky. There is a quiet, patient, and global effort underway to ensure that such a journey would not go unnoticed. This is the work of the planetary defense community, the watchful eyes on Earth. All around the world, there are telescopes, like the ATLAS survey that first discovered our comet, that are dedicated to scanning the skies every single night. Their mission is to find, catalogue, and track the orbits of near-Earth objects, the asteroids and comets whose paths might one day bring them close to our planet. This work is not driven by fear, but by a quiet, scientific sense of responsibility. It is the patient, methodical work of mapping our celestial neighborhood, of understanding the paths of all our fellow travelers in the solar system. This global network of observatories is a testament to human curiosity and foresight. The astronomers who do this work are the silent guardians of our world, patiently collecting data, calculating orbits, and projecting them far into the future. Because of their work, we now have a comprehensive catalogue of the vast majority of the large objects that could pose a significant risk, and we know that none of them are on a collision course with Earth for the foreseeable future. This knowledge is a source of profound peace and reassurance. It allows us to look up at the night sky, not with anxiety, but with a sense of calm wonder. We can appreciate the beauty of a meteor shower or a passing comet, secure in the knowledge that there are dedicated people all over the world who are quietly and patiently keeping watch. It transforms our relationship with the cosmos from one of vulnerability to one of quiet, informed understanding. Our long journey with a single, hypothetical comet invites us to gently shift our perspective. It encourages us to see our world, our planet, not as an isolated island of life, but as an integral part of a vast, interconnected cosmic system. The same physical laws that governed the comet's journey are the same laws that hold our world together and keep it in its stable, life-giving orbit. The same materials that made up the comet's icy heart are the same primordial materials from which our planet, our bodies, and everything we know was born. The event we imagined in this light was not an invasion from an alien realm. It was a family reunion, a meeting of two distant relatives who were born in the same ancient cloud of gas and dust, and whose paths, after billions of years, finally crossed. The forces of the universe are impartial. The gravity that can set a comet on a collision course is the same gravity that keeps our feet planted firmly on the ground and holds our moon in a gentle, predictable embrace. This cosmic perspective is a source of deep peace. It dissolves the illusion of separation between us and the universe. It helps us to understand that we are not just living on the Earth. We are the Earth. And the Earth is not just living in the universe. It is the universe, experiencing itself. By embracing this wider view, we can find a sense of belonging, a quiet confidence in our place within the grand, serene, and ever-unfolding story of the cosmos. As our narration draws to a close, let us reflect on the purpose of our journey together. We have spent this time exploring a worst-case scenario, a story of a cosmic impact, and yet our purpose was never to create fear or anxiety. It was to do the opposite, to use a hypothetical story as a gentle tool for fostering a deeper appreciation and understanding of our world. The true beauty of a thought experiment like this lies in its ability to illuminate the real world in a new light. By imagining a world where the sun is gently dimmed, we come to appreciate the precise and precious gift of its normal, life-sustaining warmth. By imagining a great wave crossing the ocean, we gain a deeper respect for the immense, quiet power that is held within our planet's hydrosphere. By imagining the fiery passage of a comet through our atmosphere, we learn to see that delicate blue sky as the powerful, protective shield that it truly is. Exploring what-if scenarios is an act of profound and peaceful curiosity. It allows us to safely and calmly explore the immense forces that shape our universe, to understand the delicate balance of conditions that makes our own existence possible. It is a way of appreciating the stability and safety of our world by gently contemplating its opposite. The journey we have taken was not a prediction or a warning. It was an invitation to wonder, a quiet and serene exploration of the beautiful, powerful, and resilient planet that we are all so fortunate to call home. And now, our long, cosmic journey is complete. Let us gently bring our awareness back from the vastness of space and the deep sweep of hypothetical time, back to the simple, peaceful reality of this present moment. Let the grand, cosmic images we have explored, the distant Oort cloud, the glowing coma, the silent, luminous blossom in the sky, and the slow healing of the planet, all gently fade, like a dream upon waking. Become aware once again of the room around you, the quiet sounds, the gentle temperature of the air. Feel the steady, peaceful rhythm of your own breath, rising and falling in a slow, effortless cadence. Our story was a journey of the mind, a gentle exploration of immense ideas. But the reality is that our world is safe and quiet. The sky above is peaceful. The earth beneath you is solid and still. Our thought experiment has shown us the immense power and resilience of our planet, its ability to withstand and heal from even the most profound disturbances. And that knowledge can be a source of deep and abiding calm. We live on a world that is fundamentally stable, a gentle harbor in the vast, cosmic ocean. The story is over. The journey is done. All that remains is the quiet peace of the present, the gentle comfort of your bed, and the serene invitation to rest. Tonight, we have journeyed with a messenger from the dawn of time. We saw how its path, governed by silent, elegant laws, could lead it to our world. We explored how our planet, with its deep oceans and protective atmosphere, is a place of profound resilience and quiet strength. Our story was not one of disaster, but a gentle reminder of the delicate and powerful balance that makes our world a safe haven for life. And as you rest here now, in the quiet safety of your room, perhaps you can feel a deeper connection to this patient, resilient planet. You are a part of it, just as it is a part of the vast, peaceful cosmos. There is nothing more you need to understand or explore tonight. You can let the story go. You have permission to simply drift, to let your mind be as quiet and peaceful as the deep, starry sky. Rest now. What part of our cosmic journey tonight brought you the greatest sense of peace or wonder? I would love to read your quiet reflections in the comments. Thank you for allowing me to be your guide on this gentle exploration. If you found comfort in our story, a like and a subscription helps to support our channel and create more peaceful journeys like this one. The universe is always here, patiently waiting. Whenever you are ready for another quiet story, our library of cosmic narrations is always available. For now, simply sleep well.